So for those of you who know, our whole kitchen smells of fried potato.
Nice.
It's it's quite strong. That's why we don't fry stuff too much, I think. So I started recording early today because that way I won't forget. And if anybody has any questions about anything, the whole crowd is not here yet, so this is a good time to ask. You got my full and undivided attention. And
If we
Bill,
haven't,
we
yeah,
see your mouth moving, but we can't hear you.
is
Check your
that
mic.
better?
Tom, we see
Uh,
you and hear you. Yep.
yeah, still can't hear me, huh? No.
Yeah, we hear you fine.
Okay, so quick question. If we haven't spent a lot of time on the pre-tests, are we in deep doo-doo today or are we
No,
okay? Okay.
a lot of it depends on, what your background is. And I mean, you're not taking an exam today. I'm starting from scratch,
Okay.
you know?
That's good.
So I'm gonna assume that nobody's done any prep work. That's where I always start, that no one's done any prep work at all.
Gotcha.
It helps if you did. I mean, certainly when you go to take an exam. But you notice that for this class, I figured uh, I'd give the VE the Anchorage VEs a bit of a break by not trying to schedule an exam. This one's just, people can there's a lot of options out there for people to go find their own tests. And I think, like, if you're curious, that was one of the links that I threw in there
Right.
in that email. There are so many choices you have available for finding an exam.
Okay.
So who here has taken an in-person test? Who here has taken a remote test? Okay. So let's hear your experiences in person first, because I've given in-person exams for the last 38 years.
I'm not sure if you can hear me yet.
Yep.
Let's see, my in-person test. I decided to go in person because I had a very flaky internet connection and I was afraid of losing halfway through. So I went to an in-person. It was a very organized event. The gentleman who organized it did it regularly. His three-car garage was set up as a classroom and everyone got a tablet and it was over before I knew it.
Mhm.
Very, very good experience. I also found out later that you cannot have anything at all. Now, this is regarding the remote tests. You can't have anything technology related in your view, so you have to be able to show it. And I'm using my computer right now. It'd be kind of hard to pick up the computer and show it around the room. And plus, this room is full of technology.
For
That's just
remote
my input.
exams, for remote exams, you need two cameras. So
Two.
one is usually your laptop or a computer, and the other one is a phone or a tablet or something. One camera, depending on the testing group, one camera usually doesn't cut it. So, like, we want this view, and we also will typically want another view, which looks like this one. So if anybody can see the other me,
Wave your hands. Okay.
All
so
right.
there's two of me. So there's one from the front and one from the side because I'm staring at the screen. And
Mhm.
so if you don't see the screen, you don't know what's on my screen. So the view will be something like this so that you can actually see what I'm looking at to make sure that there's nothing else untoward on my screen, like, a cheat sheet. Not that anybody's going to do it, but it has to be, you know, it's got to be above board. And I've never had somebody cheat, but there are people who have. And like I said, I've given exams in person since 1987 now. 1986, late 1986, early 87. I've never had anyone cheat, but there are people who have. So you got to, have the same standards for that as we do, for remote exams as for in person.
I've heard that one popular option is to take the test in the bathroom or in the car.
Absolutely. In the bathrooms, because you can lock the door. Because if you get disturbed, you can't, that doesn't count either. Somebody
Oh,
comes in and busts in on you.
mute the phones.
Sup, Bill?
Forgot to unmute. Yeah, I did mine remote right after I did the tech class the last time. And I did it in my office at work. I had to lock my door, had a laptop and my desktop. Had to show them, me putting my phone away. I had to take my smartwatch off.
Yeah.
But I thought it was great. My time constraints and my schedule, the online was just the best bet for me. And there really wasn't anything closer than an hour and 15 minutes away anyway. So online worked great for me.
So for all of you who are not old enough to remember, and I'm not either, before 1984, if you took anything above a novice exam, you actually had to go to the FCC office, which meant that if you lived in, let's say Eugene, Oregon, you had to drive to Portland or Seattle. Yeah, and the limit was 250 miles. You had to show you were outside of a circle 250 miles from an FCC office to avoid going in person. So yeah, and of course it had to be on a weekday. And it had to be the day that they scheduled it because, they didn't just like have a million exams open for people to take. It was the day. Uh, uh,
I have a question whether I should actually be here or not. I already have my technician class license, but I'm signed up for the general class following these two classes. And I figure I need a refresher.
That's fine.
Thank you.
That's why I'm here.
Yeah.
Me as well. I have my tech. I want to take the general, so I figured might as well have it all in my head fresh.
And I'm still getting people signing up. It's like, well, couldn't have waited more till the last minute, could you? Couldn't have waited more, even closer to the last minute. I guess 8:50 a.m. is pretty close.
Sunday isn't communion anyway.
Hey, Scott,
Hey.
one, thank you for doing this.
Mhm.
And for those that are on here, I haven't keyed in like, 6 years, and I have a general class, but I'm going to kind of refresh myself through it. And I'm also studying for the extra exam. But the reason I interrupted here or to speak is that I did get a call this morning. I have a non-critical surgery tomorrow at 11 o'clock Central. So
Mhm.
I'll probably miss that, but I will be back on for the rest of the stuff. But I will
Cool.
try my best.
Well, here's the thing. If you the day one is largely the technical stuff, and the second day is largely is largely the rules and regulations. So that's usually how it splits apart.
Okay, thank you. And I really appreciate you doing this. I mean, I think it's great.
Thank you. Well, I try. It's okay, let's see. Let's see. Is Tyra here?
Yep, I'm here.
Okay. You didn't get the large email, but if you did get the okay, is it's entirely possible that it got dumped into I mean, if you got the note in the first place that says here's the link, then you're definitely
Yeah.
signed out.
Yeah, I looked at my spam mail and all that kind of stuff. I didn't see it. But I don't
Okay.
know if it's super important or not or
Well, what I'm gonna do is just um I'm gonna send them all as individual attachments, and maybe it'll work and maybe it won't, and I'm gonna do that right now, and it's gonna be let's see.
thank you.
Here it goes.
You got it figured out? I guess I'm there. I don't know.
Somebody's here.
Oh.
I can hear someone.
Okay. Hey.
I can see.
Okay. Hello.
Good morning. Okay, so we've got about 4 minutes to go still, and people are still joining, which is good. Ugh.
All right. I'm ready.
Does everybody have a copy? Did everyone get a copy of the book that we're using? I hope. You should have
No.
gotten it. Hmm? Either electronically or otherwise.
Yes.
Okay, good.
Hey Scott, this is
Uh-huh.
Kevin. Hey, I'm traveling right now, so I'm
I
doing
see
this
that.
on my iPhone, and I'll be home in about an hour, so I'll get on the system when I get home. So I may disappear, but I'll be back.
And here's the other thing that if you're somebody who likes to, turn the camera off and turn your sound off, and I never see your face, that's okay. I'm I'm used to it. I've done this a bunch of times now, and it
Are you suggesting I turn the picture off?
no, I'm just saying if
Just
you
asking.
if you want to save bandwidth, you certainly can.
No, I'm good. I'm good.
So,
I'm through the area where we're gonna cut off, so I think I got signal the rest of the way home.
okay. Where are you?
We're on 101 coming into Warrington, Astoria,
Yep.
heading up to, we live in Ocean Park, so
Okay.
into the peninsula.
Mm-hmm.
Glad we came home this morning instead of last night coming over 26.
It's kind of windy out there.
There's all kinds of crap and trees
Mm-hmm.
all over the road. Yeah. They
Yeah.
got a snowplow out there clearing the road.
Of all the broken branches and stuff.
Yeah. Yeah.
Yeah. Yeah.
So
So again, for everybody out there, if your name on your account is like Jack's phone or something like that, change it to something that we can recognize, like a name, you know, because otherwise I don't know who you are. 8:59.
Good morning, Rick here.
Good morning.
Tina here.
Good morning, Jamie here.
Good morning.
Paul here.
Thanks, Scott.
You're welcome. Thank you. And I'm waiting for that clock to roll over. All right, you got about 15 seconds to ask any burning questions you might have. Oh, you got 1 second. All right, happy
Good morning,
shining
Elaine here.
faces. All right, good morning, happy shining faces out there. So I'm Scott, I'm N7JI, and I did start recording, which is good. That way I won't forget. And welcome to radio class. And this is the first day of a gauntlet that I've apparently set up for myself, which is 4 days because I have nothing better to do. Not necessarily true, but I enjoy doing this. This is my kind of like my after 40 years of having a license, this is my way of trying to give back. So and yeah, I really have had my license for 40 years now. So um one thing that I will say is that if you have a barking dog or a loud family or anything like that, feel free to mute yourself. If you have I also, you notice I have headphones. Headphones work a lot better than speakers because speakers and microphones tend to cause feedback. So, um, get used to muting yourself. Occasionally, I'll have to mute somebody if I hear a dog barking or I get feedback. Don't take offense to it. I'm just trying to keep the peace. On the other hand, if you do have something to say, you do have something to ask, you do have something to discuss, try to keep it on topic, but the fact that you have a question means that you're probably not the only one who's got a question. So I won't necessarily see your hand up because a lot of times I'm going to be sharing a screen or something. So feel free to just blurt something out. Hey, Scott, hey, I have a question, something like that. The other thing is that I tend to use the whiteboard a lot. I believe that a picture is worth 1,000 words, and I make a lot of pictures, so I can do a lot of talking by drawing the stuff. A lot of it is visual. It makes a lot more sense. So if you have the ability to, and everyone should, arrange your screen so that the whiteboard takes up a lot of space because I tend to sometimes get to the point where I'm drawing kind of small and writing kind of small. And it's actually fairly important. A lot of questions that you have will hopefully be answered by the stuff that I'm drawing. And if for some reason, this rarely happens, but if for some reason my internet completely craps out, I'm going to try to get back on as fast as I can. You can always just come back into the meeting. I should never get to the point where I end a meeting, so I may drop out. Again, this is not something that happens often, but if it does, it doesn't mean that I just gave up and didn't want to do this anymore. It means that something happened. So, okay. Well, before we get started, is there anyone who's got any burning questions? And yes, the email, yes, the recording will the link to the recordings. The recordings are going to be on YouTube. It's an unpublished channel, but I send the links to everybody. So, does anyone have any burning questions before we get started? Because there's a lot of material. No burning questions. All right. Making my job easy. And everybody, and it's not like I'm just talking to myself, so that's good. Okay, so the first thing we're going to do is say, wow, why do we have to do this? Okay, so the first thing we're going to do is discuss the fact that we are going to follow along with the book, but the first thing we're going to do is trigonometry. So for those of you who thought I'm never going to do math again, ha 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 ha, you were wrong. Okay, so this is a unit circle. It has a radius of 1 unit. How many degrees in a circle? And I also I also like to be interactive, so feel free to unmute yourself and answer questions. How many degrees in a circle, everyone?
360.
360. Okay. So each quarter of a circle is 90 degrees. We go counterclockwise. So as we, for instance, sit on this unit circle, if we imagine that it's a merry-go-round, it spins around this way in a counterclockwise direction. So it starts at 0 degrees. We're 1 unit away from the center at all times, and we go through 90 and 180 and then 270. The distance that we are displaced in the up and down direction is based on the angle that we have swept out, starting at the 0 degree line. So that's our angle, which we'll call Greek letter theta. So the distance up and down is the sine of the angle theta. The most it can be is 1 unit. We can also be -1 all the way down toward the bottom. There's another measure that we have, which is how far left or right we are. Also a function of that angle theta. This can max out at +1 and go to -1. This is known as the cosine of the angle theta. For the sake of argument, if we were to draw this, we would see that, so here's our, if we were to unwrap this circle and say, okay, as we start at angle 0 and then go to 180 and then to 360, we would say, okay, what is our vertical displacement? What is our sine? How far up and down are we going? Well, at 0, we're here. At 90 degrees, we're up here, and then we're down here, and then we're below ground, and then we're back up to here. Connect the dots. That's known as a sine wave. We can do the same thing with the red lines and say, okay, how far left and right are we? Well, starting at angle 0, we start up here, then we come down to here, and then over to here, and then here, and here. Okay, so this is our cosine wave. And this is our sine wave. What do you notice about these things? Considering that if you're on a merry-go-round and the merry-go-round has no reason to stop, how long will this thing be going in both directions?
Forever.
Forever. I could actually continue this like this, and I could continue the orange line for the sine like this. What do you notice is the only difference between those two?
They're out of phase.
They're out of phase. One is shifted from the other. And in fact, the shift is 90 degrees. The cosine gets there first. So really, one is just a shifted version of the other one. If we were to take the red lines and we were to move them just a little bit, we would find that they overlap with each other. So sine and cosine are both basically forms of the exact same thing. Okay, so now that we've established that, okay.
Scott,
so
I have a quick question.
Yep.
You sent us a big file there, about 10 megs or something. Is these drawing in the files?
Nope.
Okay, so I'll
Definitely
draw them myself.
Yep. It's always good to draw stuff yourself. And if you don't remember trig, this is a nice reminder. Okay, so importantly, as we go around this circle one more time, we'll find that our sine function goes like this. Again, this is known as a sine wave. And ideally, this sine wave has no beginning and no end, because as this goes around, 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 0 degrees has another name, which is 360 degrees. It also, if you're going back the other way, has a name of negative 360 degrees. It could also be 720. It could also be negative 720. So this whole thing just repeats itself over and over and over. So there's a couple of things that we can do to make this sine wave more interesting. Let's talk about stuff we can do to modify it. So how do we modify a sine wave? Well, what are some things? If I draw the sine wave, how are some ways that we can change it? Everyone?
Speed it up.
You can speed it up.
Power.
Okay.
Power.
Right? You could speed it up. Okay. What else can you do?
Slow it down.
You could slow it down, but yeah, that counts the same as speeding it up. Some other things you could do.
You can change the
You can add power to it.
You could make it bigger. Other stuff?
Ripple.
Adjust the
Yeah,
amplitude.
but remember, we're only talking about one sine wave. We're not going to make it messy. Some other things you could do to it. We changed the amplitude, which is the size, and we changed the frequency, which is the green line. We made it a faster wave or a slower wave. So what's another thing we could do with it?
Change the voltage.
Yeah, changing the voltage is the same as changing the amplitude. So let's draw this again.
Change the phase.
We can change the phase. We can change the start point and we can change the starting point. We can shift it like that. And that's known as a phase change. And we've shifted it by a certain number of degrees out of 360. And we've changed the start point and the end point. All these are ways that you can take a sine wave, which is really kind of, boring and repetitive, and make it different. You can do all kinds of things with this. So why would we ever want to do this kind of thing? Well, let's say we're going to draw our merry-go-round again. Here's our merry-go-round, and you're sitting, if it's drawn properly, always at the same distance from the center. And you're always spinning around at the same rate. So some reasons that we might want to change something is because if somebody else knows that when we changed something a certain way, it meant something, that meant that if we can do something to it and we told somebody what we're going to do and what that means, and they see it happen, that means that we just gave them a piece of information. That is known as modulation. That is how we send information from one person to another. We take a sine wave, we do something interesting with it. We go from this. We could change it to this. We could do this with it. We make it bigger and also change the frequency. There's all kinds of cool stuff we could do with it that indicate something has changed, which means that there's something different, which means that we're telling you something. Okay, so now once we've established that, we're going to go talk about our sine wave. And we're going to start to look at how it's actually built and what we can do with it. Okay, so again, here's our sine wave. Okay, so as this is being generated by somebody, again, spinning around on a unit circle and going around and around, starting at 0 degrees. Here's 90 degrees up here. Here's 180 over here. And here's 270 over here. And here's 360 up here. So that's one full wave. It's now carved out one full wave. The reason we think of this as a wave is like, we see this kind of thing in a pond. We see this in the ocean. It's a periodic thing. The fact that it's periodic means that it happens over and over and over with a certain period. So what we now can do with this is we can say, okay, well, what if I am now on this merry-go-round and I rotate one time per second? That means that I pass through 360 degrees every second. That is a period of time. So we have a period of 1 second. This is also 1 second. It's also 360 degrees. This time period is known as
Hertz.
Nope, that's our period. And it's measured in seconds. That's actually a time. How long it took to make one full rotation of that circle. How long it took to plot out one full sine wave. If I were to take this period, which is 1 second, and shorten it to a half a second, how long would it take for me to make that trip around the circle?
Half.
Half a second. Okay. Right. So instead of 1 second, it'd be a half a second. So how long would it take for me if this was now a time axis?
Good morning.
It would do this. If I would draw it properly, which I will attempt to. So now my time is half of what it used to be. What if it took 1/4 of a second for me to make one trip around? After I got done puking. After I got done puking.
It would take 1/4 of a second.
It would take 1/4 of a second, which means it looks like this. Make sure I draw that right. Okay, so that's 1/4 of a second. So as this is happening, what is happening to the amount of time that it takes to make that turn?
Shorter.
It gets shorter and shorter. Okay, so now what we can say is, well, if we have a baseline, and the baseline is 1 second, that is our baseline. That's our meters, kilograms, and seconds unit, or MKS. That's our standard unit of measure for time. It's a second. So how many times will the half second occur in 1 second?
Twice.
Twice. How many times will the quarter second occur?
4 times.
4 times. Okay. That is known as frequency. How many times something happens in a period of 1 second is the frequency. So if it takes a quarter second to complete one full circle, we get done 4 full circles in 1 second. Frequency and time or period are inverse of each other. So if we were to go around this circle 10 times in a second, how long would it take to go around once?
1/10.
It'd take 1/10 of a second. Exactly. So what we've now done is we have taken the circle and made the circle correlate to generating sine waves. And the faster we go around the circle, the faster something spins, the faster the sine wave gets generated, the higher the frequency, which makes sense. If you're sitting on the circle, that means you go around the circle. Let's say you have a period of 1/10 of a second. This means you have a frequency. You go around the circle 10 times per second. Well, as it turns out, anything per second, a thing per second has a name.
Cycle.
It's a cycle. It also was named after a person.
Hertz.
That was given the name of Hertz after Heinrich Hertz. So a thing that happens per second is known as a Hertz. So 10 times per second, if we were to go around 10 times a second, that would be a frequency
10
of
hertz.
10 Hertz. Okay. And now we also know, again, that 10 Hertz is a tenth of a second. If we were to draw that sine wave, we would have in a period of 1 second, how many waves would we see stacked up end to end?
10.
We'd have 10 Hertz. That's right. We'd have this. So that's how we generate a frequency. Okay, so now, what if we were to take this circle that we drew? Like I said, I use the whiteboard a lot. We were to take the circle that we just drew, which has 0 degrees, going around the circle like that. And instead, we take the circle and we make it so that we're looking at it like a bicycle wheel edge on. So we're going to rotate it like that. We're going to rotate it so we're just looking at a bicycle wheel edge on. And we have a glowing point, which we can see on the wheel. What are we going to see if we were to take the bicycle wheel and rotate it? It's going to start right in the center, and then it's going to go up, and then it's go back to center, and then it goes down and back up to center, because we're looking at it from the edge.
Oscillating.
Yeah, we're just going to see it moving up and down. No, it's not going to be flashing. It's just going to be moving up and down. It's going to be making a line, tracing out a line, but it's going to be going like this. It's going to hit a stopping point up top and then change direction. Going to be highest speed at the center and then all the way down to the middle, all the way down to the bottom, and then back up to the center. It's just going to be going whoop, 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 whoop. And everybody can demonstrate this by taking their phone or whatever and turning on the light and just doing this. There you go. Just a light moving up and down. Well, now what we're going to do is ask the question, does it still have a frequency?
Yes.
Sure.
Okay. What is the frequency related to?
Yeah,
How fast the
Center.
wheel is turning, right? How fast the wheel is turning around, although we're looking at it from the edge. So now what we're going to do is add an additional dimension to this. We're
Time.
now going to take this wheel that is moving up and down, right? Our light that's moving up and down on a rotating wheel, and instead of standing still, we're going to move it at a certain speed in this direction. All right. So now, as that light is moving up and down, we are also moving it horizontally. What pattern is that going to map out?
Sine wave.
A sine wave. Another sine wave. Yeah, it's going to look like this. And in fact, actually, yes, it's going to, if we had depth, we would see that it was a helix. But it actually, from the edge, it looks like this. Wow, what do you know? That's another sine wave. So now we have something which is how fast it's going up and down, which is a time period and a frequency. But now we also are moving sideways at a velocity. We're taking the whole thing and moving it sideways. So what does this actually mean? This means that we have now taken and we have managed to combine our time in seconds with our frequency in hertz, which again is 1/seconds, and combined it with velocity. What's our usual way of measuring velocity? What's our usual units that we think of?
RPM.
Well, not RPM, because that's revolution.
Miles per hour.
Miles per hour, yeah. MPH, feet per second. If we're doing metric, what are the units for metric?
Meters.
Meters per second. Okay.
Kilometers per hour.
Yep. Miles per hour, kilometers per hour, right? But typically we're going to go, because of meters, kilograms, and seconds, we're going to go in meters per second. So our velocity is going to be in meters per second, and it's going to have a direction, which is off to the right on this screen. So if we are moving something at a speed of some meters per second, and it is moving off to the right, and we are also creating this up and down movement, what we're going to have is we're going to have a frequency in some things, which are cycles per second, and we're also going to have something in meters per second. Well, what we can do, because math is cool, is we can make it a cycle or a wave per second, and we also have a meter per second. We can arbitrarily divide these things by each other if we choose to do so to create some new thing, right? Again, math is cool. We can do this kind of thing. So I am going to say that I'm going to create a new measure, and this measure is meters per second divided by cycles per second. And I'm going to call this a question mark. That's my new unit, which I just created out of the blue because math is cool and I can do that. So by looking at this, we can cancel out the per seconds. They don't exist because you have one divided by the other. So we can take these and make those disappear like that. And then I can erase them because they don't exist. Now what do I now have?
Meters per cycle.
Meters per cycle. Okay. And what is a cycle in this case? You'll remember that what made this in the first place is the frequency of how fast this thing was going up and down and back up to where it started. It looks like that. What's that? Everybody remember to mute yourself, please. So a cycle moving up and down now has another relationship to this thing called velocity. And its units is meters per cycle. So think about this now. What is a meter? How big is a meter?
3.5 feet.
About 3.3 feet. 3.3 feet. It's 100 centimeters. And what's a cycle? It's how fast the circle is spinning around, which we then turned on its side and started moving to the side. This has a name. Meters per cycle.
Hertz.
That is called a wavelength, and it is measured in meters. So we now have a wave, and it is moving at a certain speed. And we have this oscillating circle, rolling, oscillating bike wheel spinning. And as we move it sideways, that now generates a wave with a certain length. That certain length is that long. Any idea what we call that?
Wavelength.
Wavelength. Yeah. So what is it dependent on? It's dependent on how fast the thing is happening, right? How fast the circle's spinning around, and it's dependent on the velocity. Well, what determines the velocity? What actually determines the velocity in real life? So let's say I have this thing, which is a circle that is going around and around and around, and it's creating a disturbance. I take it and I turn it on its side. and I move it this way at a speed v.
Speed and direction.
Yeah. Well, but what does it have to propagate through? What is
Antenna.
this stuff? Yeah, what is that stuff? So let's make this a sound wave because there's nobody saying
So
I
this would
can't.
be air, right?
Well, yeah, let's say that this is a sound wave. Okay, so now I have this thing that is relating wavelength, which is equal to velocity divided by frequency. And we can actually redraw this as v equals f lambda. Speed is equal to frequency times wavelength. So now what we have is this wavelength equal to the velocity divided by the frequency. And we can make sure we did this right by doing meters per second over cycles per second, which gives us meters per cycle. Or sorry, meters per cycle. That is indeed a wavelength. Okay, so now that
Can no longer hear you.
Can you hear me okay?
Yeah, we can.
Okay. So
Hey, Scott,
yeah,
I just got lost there a little bit. I thought frequency was on the top and velocity was on the bottom. I thought velocity was the cycles.
velocity is speed. Velocity is like you driving a car.
Yeah, I know, but I thought we were doing meters over cycles.
Yeah, we are, because
Okay.
this is meters per second.
Okay, I thought
And
on the
this is-
previous page it was. All right, never mind.
And
I'm lost in the math.
Okay. All right. So the per seconds cancel and okay, so now what we have is we're going to say that we have a frequency. We have any musicians out here?
Yeah.
Okay. How many hertz is a tuning A?
440.
Good.
Yes, that.
440 hertz. Yes, it is. Okay.
Think on that one.
How do sound waves travel from your tuning fork or your tuner to you?
Vibration?
Vibrations through the air.
Through the air. Okay, which means that they have to travel at the speed of sound.
Yeah.
Well, it turns out that the speed of sound is about 330 meters per second in air. A sound wave is a pressure wave. It's a longitudinal wave. And okay, well, now we have some math to do. 330 divided by 440. Somebody tell me what that is. The units are meters per second divided by 1 per second. Somebody tell me what that is.
0.75.
So traveling through the air, your tuning A gives you a wavelength as it's traveling through space of 0.75 meters. That is how far apart the wave crests are as it travels through space. That hits your ear, causes your ear to vibrate back and forth, and you hear it as an A.
Well, interesting.
Okay, so now we're going to change it up a little bit. How do you make a higher pitch? Anyone play a wind instrument?
Make the frequency higher.
Yep.
AKA more air.
Anyone play a wind instrument like I used to?
I do.
How do you tune your pitch higher?
You got to make either the instrument longer or shorter or add more air.
Well, no, but I mean to make the pitch higher, you want to tune it up.
Restricted.
You
Blow harder.
Shorten up. Yeah. Well, no, we're not changing how you blow.
Faster speed.
You shorten up the tube.
Oh, yeah, makes sense.
When you're doing your first tuning, you shorten the tube. If you want to make it a lower pitch because you're a little bit sharp, you stretch it out slightly. You stretch out the instrument, and it makes a longer resonating chamber. So, obviously, if you're changing the length of the thing that's making the frequency, the frequency is somehow proportional to something physical, isn't it? If you play a stringed instrument, it's also how tightly you tension the string. But we're not getting into that. We're doing more columns because that's more applicable to radio. Okay, so frequency is proportional to the length of something that is causing it to be made. Interesting. All right, so now we're going to do another one, and we're going to make a wave traveling through space like that. It's being made the same way. Except now, what we're going to do is we're going to change the speed. And in order to make this make sense, we have to share something totally different. So what we're going to do is say that now we're going to break away from what we just drew. That thing going around the circle. And it's no longer a merry-go-round. This is now an electron. Okay, so this is where we start to deal with physics. And so here's our atom. At the center is our protons and neutrons being held together by I believe it's the weak force, or is it the strong force? I think it's the weak force. But anyway, going around this in different shells are electrons. Electrons are fundamental particles that carry a negative charge. When an electron moves, it generates a disturbance in space. An electron sitting there in space will generate an electric field because it's a negatively charged particle. If it is moving, it generates a magnetic field. So if we now take an electron and we move it back and forth or spin it around, what we end up doing is we end up generating a wave that looks just like that. Except that in addition to just generating one wave, we have something called, we'll make it the electric wave. But in addition to that, perpendicular to it, we have another wave. And we use the letter H or B for that, whichever one you want to use. That is a magnetic wave. So we have our electric wave, which is going up and down, and our magnetic wave, which is going that way. Well, notice which way I actually drew these waves traveling. I drew them traveling to the right.
Hey Scott,
Now,
what is the H and B stand for?
Those are for the magnetic field.
So there's the H and B doesn't stand for anything, or
No, no, it doesn't.
Okay.
It's just those are the letters, and electric field can either be D or E.
Oh, okay.
Question on this drawing.
Uh-huh.
Are you basically representing the electric field as being on, say, like the y-axis and the
Yes.
magnetic field being a z-axis?
Or axis, yeah, whichever axis you want to think. They're perpendicular to each other. But here's what's really interesting about this. And a pressure wave is a longitudinal wave like sound. electric waves, electromagnetic waves, you notice there's an electric and a magnetic portion to this, are transverse waves. So as the energy goes up and down and back and forth, if you hold up your right hand, it can't be your left hand. It has to be your right hand. Your thumb is the direction of the electric field. Your index finger is the direction of the magnetic field. And your middle finger is the direction of travel of the wave as it's basically going through space. So if you were to line up your fingers so that your thumb is going up and your index finger is going in one direction, then notice you now have three perpendicular fingers. That's called the right hand rule, and it describes how it's actually the cross product. It also describes how the something called the pointing vector, which is a letter S, travels. That's the direction of energy travel of an electromagnetic wave. You don't have to know this for the exam. But basically, that is the direction of travel of energy generated by an electron, which in this case is moving up and down. It generates an electric field, it generates a magnetic field, and they're all perpendicular to each other. Now, here's the other thing that is particularly interesting. What does sound require to travel?
Requires a medium, something to
It
travel.
requires a medium, like either air or water or something. And it turns out that if you have a higher density material or a lower density material, that changes the speed. Well, what does an electromagnetic field travel through?
Space.
A vacuum?
Vacuum. Yeah. What else? I heard space.
Yeah.
Wire.
Travels through air. Travels through glass. Travels through conductors. What else?
Anything that can conduct or contain.
Right. Well, that's conductors. Anything else?
Resistance.
Resistance. Yeah. Remember, we're talking about yeah. But basically, it can travel through plastic, can travel through water, and the speed changes somewhat depending on whatever this is going through. But what is most important about this is that electromagnetic waves can travel through the very first one that I drew. What is a vacuum?
Nothing.
What is a vacuum?
The absence of air.
The absence of anything.
Oh, yeah, my bad.
It's the absence of anything. It does not, electromagnetic energy does not require any medium to travel, to propagate through space. And how fast does it propagate?
300,000 meters per second.
That it has a name.
Speed of light.
Oh, speed of light.
Speed of light. It travels at the speed of light, which is 3 times 10 to the 8th, or 300 million.
Oh, I was wrong. A little off on that.
Per second. Travels through space at 300 million meters per second. Okay. Well, so now if we were to do this and say, okay, well, we're traveling at the speed of light, and I'm going to erase my space-filling pointing vector. But now we have something that's moving to the right at 300 million meters per second. Could we do the same calculations we just did a minute ago?
Sure.
Sure. We can do V is equal to F times lambda. But in this particular case, our velocity is no longer a V. It has a special name, which is the letter C, which is the speed of light, is equal to F times lambda, which is our frequency right there and our wavelength right there. So let me make sure I did that right. Yeah. Okay. Because this is 1 per second times meters, which is meters per second, which is a velocity. Okay. Dimensional analysis always makes sure that you got your stuff right. Okay, so in this case, our speed is now 300 million meters per second. So we're going to do a very basic, we're going to draw something that's going to help out a lot in case you forget this. Everybody ready? We're going to make a circle. And in the circle, we're going to put 300 million and F and lambda. Whichever one you don't have, you cross out. So let's say that we have a wave that is an electromagnetic wave. So how fast is it traveling through space?
Speed of light.
Which is 300 million meters per second, which we wrote in there. So that doesn't change. That's true for everything. And we have an electron that is moving up and down at a frequency of 1 hertz. A very slow electron. It's a very slowly moving electron. Well, okay, we know our frequency. We don't know our wavelength. We're going to cross out the wavelength. So our our wavelength is equal to 300 million divided by, because we have a division bar here, by 1. How long is our wavelength?
300 million.
300 million meters long. The electromagnetic wave that we generate that is traveling through space is going to have a periodic, it's going to hit crest to crest, start to start, basically just repeat every 300 million meters. That's a pretty long wave, isn't it?
Mm-hmm.
That's a really long wave. 300. It's gonna carve out a path 300 million meters long, or 300,000 kilometers, which is about the distance from here to the moon. Pretty far. So we don't usually work in terms like that because we don't make electrons go up and down once per second. I mean, that's pretty unusual. Electrons are really tiny. We usually oscillate them a lot faster than that. So what we're going to do instead is say that we're going to instead have an electron that moves up and down and does what we want it to. But instead, we're going to make it 1,000,000 times a second. So we're going to make our circle again with our 300 million.
Are there any benefits or negatives to having it move faster versus having it move slower?
And now we have a frequency of 1,000,000 hertz. So what would our wavelength be? Well, we don't know our
300.
wavelength. We cross it out. We have this division bar, and then we have 300 million divided by 1,000,000, which is
300.
300.
3 meters per second.
300 meters
per second.
Okay.
Hmm.
Well, that makes a little more sense, right? That's at least a number that we can kind of put our hands around, so to speak. I mean, it's about 1,000 feet. It's a physical length. That wave that gets made is roughly 300 meters long. That would be the wavelength. Now, what do you notice about this calculation right here? What do you see in there that really is kind of annoying?
A lot of zeros.
All the zeros.
Question when you have a moment.
What in there is sort of annoying to deal with?
All the zeros.
Can you hear us?
Oh, do I still have movement?
Can you hear us?
Did I freeze up there?
Yes.
No.
All the zeros.
I can't hear. Hold on. Why can't I hear? Hold on.
Testing. Can you hear now?
We hear you.
We can
Can
hear
you
you,
hear us
Scott. We
now?
can hear you, Scott.
Hold on a second. Okay, now I can hear. Try again.
Hey, all right.
I don't know
All
how
the
I managed.
zeros.
I don't know how I managed to do that.
All the zeros.
All the zeros. Those are really annoying zeros, right? Okay, so what we're going to do is we're going
Question
to.
when you have a moment.
Yeah, go ahead.
Okay, this is all fine in a vacuum, but how do you now take account for atmospheric interference, fog,
Yeah,
rain, snow?
air. Honestly, they don't change things that much. Air is very, very close to a vacuum when it comes to electromagnetic fields. So you basically can approximate it that way. All right, so now what we're going to do is we're going to redraw this. And we're going to say that we, instead of 300 million and 1 million and lambda, well, okay,
Well,
we can.
megahertz.
Everybody hears me okay?
Mm-hmm.
Okay. All right. So now what we can do is we can say that we're going to use our powers of math here, and we're going to say that this is actually 1 times 10 to the sixth power, or 10 times 10 times 10 times 10 times 10 times 10. It's a lot of zeros thrown in there. But up here we have 300 times 10 to the sixth, or 300 times 10 times 10 times 10 times 10 times 10 times 10, and these all cancel out. So we're left with 1 over here, and we're left with 300 up here. The only thing is that since we got rid of those, there's an implied big letter M, which is 10 to the sixth, and there's an implied big letter M here, which means mega, which is 10 to the sixth power. Well, as it turns out, most of the stuff that we're going to work with is not in the hertz, it's in the megahertz, which means that we can actually do that. We can sort of just like say, okay, well, it's megahertz, and we're going to get rid of these remaining 6 zeros. So we're going to redraw the circle like this. So that is now the circle that we redraw. So now what we can do is we can say, okay, let's take a frequency of 10 million hertz. What's another way to rewrite that? It's 10 times 10 to the sixth, because we have 1, 2, 3, 4, 5, 6 zeros we get rid of. 10 to the sixth is
10 megahertz.
10 megahertz. So, because 10 to the sixth is the big letter M, this is where we start using shorthand. There's a lot of shorthand because it's not because it simplifies our writing quite a bit. So this becomes 10 megahertz. Okay. So now we have 10 megahertz, and we can plug it in there. We want to know what our wavelength is. We don't know it. And we're left with our wavelength in meters is 300 divided by 10, which is 30 meters. So we're getting down to something physical. We're now at 30 meters, which is about 100 feet long. So what we've now managed to do is simplify our circle, simplify our calculations quite a bit. And now we are actually relating something at a very, 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 very high frequency to something that has a physical length, which has a wavelength of 30 meters long.
I had a question
Yep.
earlier when you couldn't hear us, but so what is there a benefit to having that wavelength shorter didn't say like the 300 million, like to the
Oh
moon,
yeah.
like having.
Well,
Oh, okay.
yeah. So the question is now, okay, remember what physically made that thing happen? What made that electromagnetic wave?
Big Bang.
Electron going in circles.
The electron going.
Electron going back and
Electron
forth.
going back and forth.
Right. So if I want an electron to move back and forth, that means I need to have something that physically constrains it so that it moves a certain distance. That's known as an antenna.
Okay, gotcha.
So now my wavelength is proportional to the length of the antenna that I have constraining the electron. So the longer the wavelength, what does that say about the antenna?
Long antenna.
Big antenna. So long wavelengths, big antennas. Short wavelengths, small antennas. They all have certain reasons for that to exist. There are lots of reasons for big antennas and small antennas to exist. There are lots of reasons for all those wavelengths to exist. But now, here's the really interesting thing to me. Okay, this is, if everyone can still hear, this is a map. Does anyone know what this thing is called?
That is the radio spectrum.
No, it's not the radio spectrum.
Electromagnetic spectrum.
It's the whole electromagnetic spectrum from end to end. What do you notice on there that is of interest to us as humans?
We can see very little of it.
We can see very little of it, but we can see some of it.
Yes.
Right? How are radio waves, which are at the very left end, related to those different colors of light?
Well to the left.
They're well to the left. What does that mean? Look at the top line.
Much slower frequency.
Frequency.
Much lower frequency, much longer wavelengths.
Mhm.
Well, as it turns out, as you go from left to right, all the way at the right end of things are X-rays. What do we know about X-rays?
They can see through things.
They can see through things.
They go through things.
Why can they go through things?
They're very small.
Well, but even beyond that, they're also very high energy. They have a lot of energy. The energy of the photon that carries that wavelength, that carries that energy, goes from very low at the left end to very high at the right end. And that is why, for instance, when Einstein was working on the photoelectric effect, it turned out that you could illuminate something with red light. You could illuminate something with a really bright red light and nothing would happen. But if you changed it to purple light, it would. And even if it was just a little bit of purple light, because it has to do with the energy of the photon that's carrying the energy. That determines its color, that determines its wavelength. Radio waves are very low energy, and all those other ones to the right, in particular, like ultraviolet and X-rays, which are the ones that cause mutations and cancers and things like that, because they have enough energy to actually rip apart DNA, whereas radio waves don't. And by the way, if you're curious, this is actually in your in the packet that I sent you guys. So,
Yeah, it's in that zip file.
yeah. So what's really important about this is to realize that all electromagnetic energy is the same. It's fundamentally the same thing. It travels the same way. When you send out a radio wave, you are basically making waves that the energy is carried in photons the same way that light works. So light waves or light or photons travel in straight lines. How about radio waves? This is a fundamental of physics.
Yeah.
They do too. Yeah. Radio waves are the same as light. They're exactly the same thing. The only thing that's different is the frequency and wavelength.
Makes sense.
Yeah. So now that we've established that we're really talking about the same thing, what we can do with these things is we can make them behave in different ways. So for instance, what's a mirror?
Reflection of
Reflecting image.
Yeah, it reflects light. Okay. Could there be a radio mirror?
yes.
Yeah.
Sure. Right. It might be a little bigger or look different. Right. Has anyone ever taken a
Troposphere.
Yeah. Well, any number of different things. Has anyone ever taken a spoon and put it in a glass of water and noticed that the spoon looked bent?
Mhm.
Yeah,
Okay, why is that?
because the
Because
light
the
is
water is
bending.
altering the wavelength.
Yeah, the water is altering the speed.
Diffraction.
Yeah, it's changing the speed that the light waves are traveling in one direction, which makes the light waves look as if they're going a different path, which in fact they are, and it makes the light look bent. Well, the same way that works, you think it can work with radio waves?
Yes.
Sure.
Sure. That's the same reason that's the same reason that we end up with these things called rainbows. That's the same reason that we end up with prisms. Basically they're just different colors. So, is it possible to make an infrared spectroscope? Sure. It's a different color of light. You can do the same thing with radio waves if you really wanted to. So now what we're going to do is put this back up on the screen, and I'm going to zoom in on the right-hand side, and I'm going to ask now, what is the difference between, let's say, red and yellow and red, orange, yellow, green, blue, indigo, and violet? Fundamentally, what is the difference?
The frequency at which the
color.
Right. Frequency, wavelength,
The energy.
color. Okay, so how come to us red is red and blue is blue? Why?
That's the least absorbed off whatever it reflects off of.
Right, but fundamentally, why do we see them as different colors?
Because blue has
Our eyes
a
perceive.
shorter wavelength.
Our eyes are built for it.
They're the cones.
That's right. Our eyes are specifically built so that red, orange, yellow, green, blue, and violet, even tiny changes in color, we are very sensitive to. Right? How come we can't see ultraviolet? Bees can. Bees can. Bees can.
Our eyes aren't made to do it.
Yeah, right. There was no reason for it, so they don't do it. How about infrared? There are animals that can see infrared.
Well, we can only see red, green, and blue.
Right. That's right. And all the others are combinations of their, different rods and cones. But we can tell that the combinations of things make different colors. So why can't we see infrared? Because our eyes are not built to see infrared. Okay. How come we can't see radio waves?
Out of our range.
It's out of our range. That's right. That's really it. I mean, basically, we can't see infrared. However, can we build an infrared camera?
Yes.
Yes.
Yeah. Right. Which translates it into some place that we can see. Can we build a radio camera?
Oh, yeah.
Sure.
Yeah. Any idea what a radio camera looks and sounds like?
I've seen the radio telescopes.
Big telescope.
Yeah. How about another thing?
Well, ham
Like
radio.
a dish.
That's right. It's a ham radio. Here, right here. So I'm going to open up this web SDR. Can everybody hear that?
Mm-hmm. Yes.
Yes.
Can't understand it.
So basically what we're looking at is a swath of the radio spectrum being moved to someplace that we can see. Notice these are frequencies. This actually is 28.15 megahertz up to 28.35 megahertz roughly. And these are the signals that are being received by this particular web software defined radio, or SDR, that's in Utah at this present time. If we were to go to a different frequency, let's say down here, and turn them on. Any idea what that is?
Morse code.
Morse code, right? And that's being sent on one particular frequency, which we have built a device now, which is converting that particular frequency to something that we can hear and see on the spectrum. This little swath of spectrum between 28.031 and 28.032 megahertz can be found right here. On this, it is one tiny little piece of this huge electromagnetic spectrum, which goes from negative infinity up to infinity. That particular place that we were just listening to is somewhere right below 30 megahertz. That is in this particular spot. That's what we are able to see. We have names for this for certain sections of the spectrum. Notice we have this thing called HF, which is high frequency. That goes between 3 and 30 megahertz. VHF is very high frequency, goes between 30 and 300 megahertz. And UHF, which is ultra high frequency, goes between 300 and 3000 megahertz. And notice we use the big letter G. Mega means million or 10 to the 6th. Giga means billion or 10 to the 9th. So that little piece of spectrum that we were listening to is this tiny little piece of the bigger spectrum. Now, of some interest to me as well is the fact that we have figured out what to do with a lot of these pieces of the spectrum. One of the things we can do with it is we can split it up into usable chunks. And somewhere I have this usable chunk. There we go. All right, so we are going to share this, and then we're going to take a break because I know everybody's probably, there's a lot of information to take in.
Having a headache by now?
Oh, I hope not. Okay, so here we go.
Somebody needs to mute because it's looping.
I got it. There we go. Okay. This is the frequency spectrum allocation in the United States. And let's see, someone's still echoing a lot. Please mute yourself. Okay, there, we got it. Okay, so notice we have this range that goes from 3 megahertz up to 30 megahertz. That has a name. Does anyone remember what that's called?
HF.
High frequency.
That's HF or high frequency. But notice that within that range, this is split up into a lot of different things. Okay, so how much space is there between the 3 megahertz and 30 megahertz in megahertz? Between 3 and 30.
27.
27. Okay, so we have a bandwidth, an available bandwidth, as it's called, of 27 megahertz. So within this 27 megahertz are all of these different services that end up having to share that limited spectrum. So now we're going to go down to the next segment. Well, it starts at 30 and goes up to 300. How much space is there between 30 and 300?
270.
270. Yeah, okay. So even though it's drawn the exact same way, there's actually 10 times more room there.
Yeah.
That bandwidth is a resource which is then used for, well, take a look, all the things that use it. This is just the United States. These are all services. And oh, look at that. We have FM radio between 88 and 108. Anyone ever listen to the radio in the car? There you go.
All the time.
Yeah, and here, just to the left of that, TV channels 5 to 6. And notice they take up a lot of room. TV channels 2 to 4, they take up a lot of room. But then there's all this other stuff. Oh, look, up here at 144, here's the amateur band. This is what we call the 2-meter band. And why is it known as the 2-meter band?
2 meters between it.
Because
144 and 146.
Between what's 144 megahertz? What's 300 divided by 144 approximately?
2 point something.
Yeah, like 2.05. So we call it the 2-meter band because the wavelengths are about 2 meters long. Okay, so here's the end of that band. So now we're going to look all the way to the left of the next band. 30 to 300 was called VHF. This one's called UHF, and it goes from 300 up to 3000, which is known as 3 gigahertz. And look at all the users in here.
That's compressed.
It gets more and more compressed because how much space is there in here between 300 and 3000?
Lots.
2700. There is 10 times more bandwidth available in this band than there was in the previous one. Okay, so a fixed service can be like telemetry and stuff like that. But look at all these different things. Notice as we start to get up here, how come we get into radio astronomy and we get into a lot of satellite stuff? Here's a satellite thing. Here's more satellites. How come we put our satellite stuff up here? How come, for instance, we have an amateur band right here, but then we also have this fixed and mobile and radio location right in this range, 2417 to 2450. This is where Wi-Fi is. 2450 and up. How much room is there between 2417 and 2450? 33 megahertz. That's actually a lot of room. That's actually more than there is on this entire piece. Just on that one section. So that is why we do things that require a lot of bandwidth, like Wi-Fi. That's why we put them up in these areas where there's a lot of room. Well, as it turns out, there are certain advantages like that, but there are also certain disadvantages. The disadvantages are how these waves travel through space. So in order to send, let's say 3 gigahertz up to 30 gigahertz, take a look at how much stuff there is up here. That is some pretty coveted bandwidth up here. There's between 3 gigahertz and 30 gigahertz, there's 27 gigahertz, which is 27,000 megahertz of bandwidth. So the higher the bandwidth, the more information you can put there. So if you were to do that, for instance, you have lots of services that want to transmit a lot of data. Can anyone think of any services up in space that would want to transmit a lot of data so that you can get music or you can have a satellite phone call?
SiriusXM,
Starlink. Yeah, Starlink is a good one. Any satellite communication service that is high bandwidth that people want to be able to do streaming on, for instance, or terrestrial stuff that people want to do streaming on, you want to put that where there's a lot of room to put it, where there's a lot of bandwidth available, which is why those frequencies are very, very coveted. People pay a lot of money to get access to those frequencies because they can put very high bandwidth services up there. Everybody ready for a 5-minute break?
Sure.
Okay. All right. 5-minute break.
Anybody out there still hanging around?
Yes, sir.
Hey, he
Yes.
said some of them bandwidths are highly coveted. Does that mean people like have their amateur license, something that we can't get on? Is that what he's talking about?
He's talking about commercial access.
Okay.
So that has nothing to do with amateur radio at all. It's to do with the commercial people who want to do Wi-Fi. They want to do internet. They want to do all kinds of things like that. It's mostly on internet related stuff.
Okay. Okay. Thank you.
People.
The short story is that's where the FCC makes their money. They allocate that bandwidth for certain users, and then there's licensing fees that are associated with that. So Verizon, for example, owns a portion of the band. Satellite users own a portion of the band. So it's really marketed out there as a whole, and ultimately they're the ones that decide how that gets divvied up.
So let me ask a question.
Yeah, and unfortunately, 90% of it, they buy it and just sit on it, so it can't
That's
be
right.
used.
Right. But now let me ask another question while we're thinking about that. Okay. So we have all of this space. Anywhere that you see, and by the way, we're not, class isn't back yet. We're just talking. Anywhere you see this kind of like an aqua green color says amateur, right? So take a look at all the different aqua green colors that you see. 902 to 928, 1240 to 1300. There's stuff over here. There's another band up here. Ooh, a whole big band from 2390 to 2450. That's up by Wi-Fi. Oh, here's one at 24 gigahertz to 24.25. Here's a shared one from 24 to 24.05. That's a lot of space. Here's one at 241 to 248. Notice it says amateur. So what does that mean that we can do with these things?
Use them.
Yeah, we can use them for pretty much anything we want that's within the law. Your license. Oh, look, here's a huge one. 75 to 81 gigahertz. Amateur satellite, amateur terrestrial stuff. We have, let me ask, how much do you think this is worth money-wise? If let's say that a satellite company were to say, oh, we are willing to, we would really like that. Oh, 6 gigahertz up there between 75 and 81 gigahertz for a high bandwidth communications. How much do you think that's worth?
Billions. Billions.
Billions of dollars. Okay, so why don't they have it?
Because the ARRL lobbies Congress and keeps them from getting it.
Pretty much, yeah. So we have this thing called the American Radio Relay League. And the ARRL is our voice in front of the FCC and in front of Congress to say that, you don't get any tangible assets money-wise from us, from all these 750,000 hams in the United States. But what you do get is you get a lot of innovation, you get experimentation, you get people developing new techniques. And when the chips are down, you get 750,000 people who are willing to go and do emergency communications and use all these frequencies that we have for the good of everybody in our country, for the good of everybody in the world, which we do. So who pays for that? Who pays for them to go do that?
Members.
We do.
That's right.
dues.
Okay. So the American Radio Relay League has about 140,000 members now. And how many hams are there in the United States? 750,000. So basically, I'm also very, very involved with the American Radio Relay League because I really believe in the mission. I believe in the numerous missions, the biggest of which is protection of these frequencies that we are able to use free of charge, with the expectation that we're going to be able to give back when the time comes and be able to keep developing things. But if it's a if you have an opportunity to join ARRL, I strongly recommend doing it because everybody who benefits from the ARRL doing what they do is going to be able to get access to frequencies that they actually want and need and enjoy using without having to worry, hopefully, too much about, those frequencies being coveted by AT&T or Verizon or some satellite company that wants to do something. Remember,
Hey, Scott.
they have basically unlimited budgets and unlimited numbers of lawyers, and we don't. Yes.
Hey, do we have to have our license to become part of the ARL?
You don't. I think you can't vote, but you don't need to have your license yet to join.
Thank you.
I have a maybe related question. I'm not sure. We had a pretty bad winter storm here.
Yep.
We lost everything. I'm a police chief for private police department. Our IT guy has everything running off the internet, and we lost internet. So none of our computers work. All we had was our radios, right? I had a suggestion from someone that we get Starlink so that we don't lose our internet.
Yep. It's actually a very valuable tool.
So my IT guy is against it and keeps saying that the speeds are slower because it's set. Is that true? Is it?
I don't know that it's necessarily slower, but everything is proportional to how many people are using it. They're inversely proportional.
Gotcha.
Well, that's true, but
it's still pretty fast.
Gotcha.
Can I throw in just
something in here as an ISP? Starlink is fine for different things, but your IT guy should have set you up so that you were self-sufficient and not use the cloud. Anything that has critical assets should have their own copy with cloud backup.
As someone in IT,
Go ahead, Rachel.
cybersecurity, I 100% agree with that. Especially for police, you should have some kind of a dedicated line to your ISP. Now, if we're talking that, your entire ISP is gone down, like we're talking major natural disaster, Starlink is a fine backup. But the thing is, yes, it is going to have slower speeds because you have to think about the latency, the time for you to send a request, just a simple ping from your computer, that now has to be sent all the way up to space. And now we have to consider, you said it's winter, so it's storming, it's snowing. You've got a lot of things that are going to interfere with that beam. It's got to get up to the satellite, and then it's got to come all the way back down. So something that would be maybe just like a normal, 17 millisecond transaction is now going to be like 170 milliseconds. And then the reduced bandwidth. So it's fine for emergency situations, but as another IT person, I think you should, reconsider your infrastructure.
We had no phones. Our phones are IT based. We had no telephones. We had nothing. You know what I mean? So yeah,
redundancy.
Yeah. So I know that there were a lot of Starlink deployments in North Carolina, but I also know that in North Carolina that there was, if you think about it, there were ways of getting information out from point to point, but not everybody has Starlink. So out of a general area, that's true, but not everybody has one. So there was a repeater operating on 2 meters in the area, and for about 10 days during the daylight hours, they were, I think, running off of solar and generator power, and they were basically just taking, it's called health and welfare information, and it doesn't seem like that's a big deal, but if it's you and you're trying to find out what happened to your relatives, getting information in and out of an affected area from places where there's no other communications, people say ham radio is, archaic. In a lot of ways it is, but in a lot of ways it's not. And in the ways that it's not, it's very good at what it does because it relies on people, and it relies on people who are trained and know what they're doing to do what they do. So You know, there were a few people who were basically running a daytime net that lasted for 10 days. And they say, hey, you know, here's the guy down the street. He's not a ham, but here's a name, here's a phone number. Can somebody please call him? You know, can somebody please call his relatives and tell them that he's okay? Because they haven't heard from him in 6 days. So
God, you may want to mention at some points mesh networking.
yeah, well, MeshNet, we'll get to that later.
Sure.
Yeah.
I think it'll be interesting for a lot of these people.
We use cellular modem as our backup. What happens if the cell sites go down? That happened in the Carolinas. The whole cellular network went down. So, yeah, I mean, it's a good backup until, okay, you need a backup for your backup. So, all right, ready to get back to radio stuff? Here we go.
Thought we were.
Yeah, we are. Oh, radio theory. We're getting back to radio theory. Okay. So I'm actually doing an equivalent of jumping around quite a bit in the book. If you're trying to follow along with the book, it gets a little tough at this point because the first part of the book, I don't like the order of events quite as much as I like it toward the end. So all the stuff that we're talking about is actually covered in there. And all the questions are there and et cetera, et cetera. So, but what we're going to do now is we are going to, if anyone's curious, we're on the equivalent of what's like page 35 in the book. And the book, when I bring this back up, it looks kind of like this. Here we go. Notice we have radio wave characteristics. So now we're into dealing with radio waves and things like that. So like I said, we're going to bounce around a little bit, but there's a good reason for it. I think it makes for a good narrative. Okay, so we now have this radio wave that is traveling through space. All right, there's an electric field, and then we're also going to have a magnetic field perpendicular to it. The wave is being generated right over here on the left-hand side by something which is moving back and forth. Going to have an electron moving back and forth, which is generating an electric field and a magnetic field that is propagating through space. Propagating is how things move from place to place. So in order to do that, we have to somehow have an electron that can move back and forth in a particular area. In order to do that, the electron has to be able to generate a full wavelength. By the time it goes from one end to another and back and forth, it has to generate a wavelength. This wave that you see here is actually a disturbance in space, if you want to think of it that way. It is a field that is propagating with energy through space, which was caused by the movement of an electron. So if we now take this electron and we can take a copper atom, which has a bunch of electrons flying around the outside. This copper atom has on the inside protons and neutrons and electrons zipping around the outside. Well, as it turns out, this copper atom has electrons which are not particularly tightly bound toward the outside. There's a little bit of shielding of the nucleus, which means that electron toward the outside, it's pretty easy to pull away. So if there's another electron that happens to be in the vicinity, that electron can kind of be sucked into the atom. And what'll happen is that this one will slowly drift away. Well, if there's another atom nearby, which is copper, that electron will drift into and become part of that copper. When that happens, well, there was another electron there. I guess I'll just drift away. So now we have an electron starting on this end, on the left side. What ends up happening on the right side?
Keeps going.
Keeps going. Well, if we have this happening a billion times, it happens really fast. So if that's the case, and we take that piece of wire, which is made of copper or a block or whatever, and we treat it as a black box, we dump an electron in here, what happens on the other side?
One comes out.
One comes out. Well, as far as we're concerned, we don't really care what's happening inside, practically speaking. I mean, it's not instant, but it's really quick. That movement of electrons is called a current. Motion of electrons is called a current. The material that this is made of has a lot to say about that current. We have to push, letter I is current, we have to push an electron with a certain amount of force. This is known as electromotive force or a voltage in order to get that electron to come out the other side. This characteristic of this stuff is called resistance. So as we push electrons with a certain voltage, that determines how much current flows based on the resistance of the material. There are multiple different kinds of material. Something that allows current to flow easily is called a conductor. And something that does not, I'm going to do it in red. Different red. Is known as an insulator. So a conductor has very low resistance, and an insulator has very high resistance. We measure units of resistance in ohms, named after Georg Simon Ohm, another one of those early engineer physicist types. We measure volts in units of volts, named after Alessandro Volta. And we measure current in amperes, the big letter A, after ampere. Okay, so let's think about it and let's name some good conductors.
Copper, aluminum.
Copper. Other ones? Gold.
Silver.
Other ones? Silver, Ag.
Anything, most things metal. Most things metal.
Most things metal. Not all, but some are better than others. But we've got aluminum. Yeah, aluminum's actually really good, but why don't we use aluminum as a conductor most of the time?
Doesn't it have an easy melting point?
No, it's actually fairly high.
Corrosion?
Yeah, this actually makes Al2O3 very, very quickly on the surface. Aluminum is actually very reactive. And what happens is that you get a surface of aluminum oxide on the aluminum, and aluminum oxide is not conductive. So what you end up with is a very high resistance surface.
In the 70s.
Burning houses down.
Well, that, but in the 70s, they used it in what do you call it? Wiring for automobiles.
Yeah.
And talk about a bad deal because you can't solder it.
Right.
So how do you replace? How do you repair it? You know.
Yeah.
Big time problems.
Well, in New Jersey in the 1970s, in order to save money, they would take an aluminum wire and use house wiring, and they use another aluminum wire, and they thought they would just wire nut them together. And what would happen is that you'd end up with a high resistance connection between the aluminum oxide inside the wire nut. So what would happen to that? You have, 15 amps flowing through your house, and you have high resistance, and we're going to get to Ohm's law very shortly. This makes a lot of heat. And you had a string of houses in New Jersey that
Burn.
burned to the ground. Yes, because of improper use of aluminum. You can use it, but there are special techniques that need to be used. Okay, other things that make poor conductors, which are good insulators.
Glass and ceramic.
Ooh, glass. I like that one. Ceramic,
Plastic.
plastic. Depends
Rubber.
on the plastic, but sure. Other
Wood.
ones? Rubber.
Wood.
I heard wood. Ooh, I heard air. Good one.
Micah.
Mica, yeah, rock. Certain kinds of rock. Mica makes really good capacitors. Okay, so there are lots of things that make very good insulators. Okay, now how about somewhere in between? Things that are in between, good and bad.
Silicon.
We call those semiconductors.
That's called a semiconductor.
Tin.
Freshwater, saltwater.
Well, salt water is a great conductor.
Tin.
Salt water is a great conductor.
Right.
Deionized water is a terrible conductor.
Cubic boron.
Hmm?
Cubic boron arsenide.
I'm going to have to take your word for it, but it's an arsenide. So, yeah. So, silicon, arsenic, gallium, AS, there's germanium. Those are good semiconductors. So, yeah, boron, phosphorus is a little bit of a conductor. So, we usually use these as doping agents. So we have our voltage here and our current here. And a semiconductor typically is going to be somewhere between a conductor and an insulator. So what we do is we take this material, which very often is silicon because there's a lot of silicon. What's the most common source of silicon everywhere? Sand. Yeah, there's silicon dioxide. There's a lot of silicon out there. A lot of sand in the world. So what we do is we start with our silicon and we have intrinsic material, and we typically will go and we will dope this material with some pluses, which are lack of electrons. These are known as holes. And over here, we do a few extra electrons. This is known as P material. This is known as N material. And now we have something that looks like this. Or that looks like that, which is known as a diode. And what we can do is we can take our stuff that conducts kinda, and by tilting the table a little bit, we can make it so that current goes through in one direction, but not the other, preferentially. This is known as a diode. And the direction of flow is that way. Okay, so now one thing that's important is we're going to draw what's known as a schematic diagram. And you may be wondering, why are we doing this? Well, there's actually a reason for this. Okay, this is a schematic diagram, which is a battery and a resistor. A battery is a source of electromotive force. Battery has a voltage. It has electromotive force. If you think about that term, it is electromotive, which is moving electrons, and it's a force. It pushes our electrons around the circuit. In doing so, it generates a current, which is the movement of electrons, based on what the resistor is, how the resistor is built. Now, because it's measured, the term is electromotive force, we usually use the letter E for a battery or for voltage. Now, just to be confusing, what charge is on an electron?
Negative.
A negative charge. So where do all the electrons you think come from on this battery?
In actuality, it's a negative.
Negative.
Yeah, okay. So which the electrons are actually going this way, right?
Correct.
Kind of makes sense. They go from where there are more to where there are less. That makes sense, right? Well, unfortunately, at one point it was not really known what charge electrons were because they hadn't discovered the electron yet. That wasn't discovered until J.J. Thomson, which was a lot later than Michael Faraday. So what happened was they got it wrong. And they assumed that current actually by convention flew right out of the plus and around back to the minus. I mean, it kind of makes more sense, right? If this is 9 volts and this is at 0 volts, things would go from higher to lower. That makes more sense, right? So this is how we calculate current in circuits. Even though we know that electrons come out of the minus, our current comes out of the plus. We're basically still living with a mistake that was made about 180 years ago. But this is what we're left with. So we would just have to keep in mind that electrons come out of the minus, but electrons are really tiny. So, we're just going to kind of ignore it for now and work from there. So by convention, electrons come out of the plus, or sorry, current comes out of the plus and goes around to the minus. We have a name for this point at the minus sign. We could draw this. Our 0 volt reference for a circuit is known as our ground. Ideally, if you think about it, if you think about the surface of the Earth is pretty big. It's assumed that it has no charge. It's at 0 volts, even though the whole Earth may be charged compared to another planet. For the sake of us living on the Earth, ground is equal to 0 volts. That is our reference point. So as we go around this circuit, there's a couple things to note. Number one, when you go around a circuit, if you start at 0 volts, for instance, and you go in the direction of the purple arrows, you add voltages and subtract voltages. And what does it have to be when you get back to where you started?
0.
It has to be right where you started. This is called Kirchhoff's voltage law. And what we do is we start at 0 and we have a battery. A battery is a source of electromotive force or potential, and that's plus 9. Now, we have a resistor. We'll call this voltage drop because resistors resist. We're going to say minus VR. And then we're all the way back is equal to 0. So yeah, VR is equal to 9 volts. So that means that all of the voltage that is supplied by the battery is now completely taken down by the resistor. So if we were to measure the voltage across this resistor, we would find that it's 9 volts, and physics holds true. So we have a 9 volt measurement across the resistor. If we were to take another resistor and add this resistor right here, I'll use a different color. We now modified the circuit. We would make this VR1 because that's the first resistor, and this is VR2. And we go around the circuit because this is R2. A circuit comes from the word circle. So we're going around the circuit just like a racetrack. And we go plus 9. We'll go purple. And then minus VR1 minus VR2 is equal to 0. So that means that VR1 plus VR2 is equal to 9 volts, which means that the voltages that are dropped by the two resistors have to be equal to the source voltage. Well, okay, that makes sense. I think everyone will agree with that. But what does that mean about these values? Well, in order to figure that out, we need to do something called Ohm's law. This is one of the 3 circles that we're going to make. Remember that first circle, which was 300 F and lambda? And believe it or not, all this actually does come back and connect in just a minute. All right, so there are 300 F and lambda, right? That was our first circle that we did. We're going to do another circle. E, I, R. Okay, this is our volts, this is our amps, and this is our ohms. The reason I do this is because the formula is E equals I times R. So unless you're really good at remembering which is which form is which, say, okay, well, let's say I don't know my current. Well, I can cross this out. I still have this divisor bar. I is equal to E divided by R. It just makes it a little easier to remember which comes, which goes where when you're calculating, when you're changing the form of your equation. So now, because we have determined that we have accepted, I'll say, that Ohm's law actually works, what that means is that if we have a current flow out of the battery in this direction, let's look at all the things that current has to flow through in order to get back to the battery. What's the first thing the current has to flow through?
The wire.
Yeah, the wire. We're going to assume the wire is perfect. So it has no resistance. What's the next thing?
Resistor.
Resistor
R1.
R1. Right? So it goes through resistor number 1. Okay. And what's the next thing it has to go through?
Resistor.
Another piece of wire, which we're going to assume is perfect. And then after that,
PR2.
the other resistor. And then through this other piece of wire, which we're going to assume is perfect, which is then back to the battery. Well, what that means is now, if these I's are all the same everywhere in this circuit, this is known as a series circuit, then, and E equals I times R is true because we've established that E equals I times R because Ohm's law says that it's true, and it's been proven a million times. Then if E equals I times R, then this resistor and this resistor, if those are exactly the same, then the voltages experienced by both of them are not necessarily equal because they're going to be proportional to the values of the resistors. So this is known as a series circuit. As the current flows around the series circuit, the voltages experienced by each of those devices will be different. Each of those resistors will be different. This is how, and this is why I bring this up. Did anybody put up any Christmas lights this year?
Oh yeah.
What happens if a light blows out?
The whole string shuts down
Okay, why does the whole string shut down?
because it breaks the circuit.
Because that is the equivalent of doing. Oops. That is the equivalent of doing this with your circuit. And opening up your circuit so you have an open circuit, which means that no current can flow. This is the extreme form of a series circuit, and that's why your dead bulb, which now blue, takes down your entire string of Christmas lights. Now, the other thing, of course, is if we were to redraw this and we have our battery like this, and we have a resistor here and a resistor here, There's another thing called Kirchhoff's current law, which says that the current that's flowing here, if it hits a branch, some of it goes this way and some of it goes this way. Well, if this battery, let's say, is 9 volts, how much voltage is available right there? How many volts?
9.
9 volts. How many volts are available right here?
9.
9 volts. It's the exact same thing. Which means that if this is R1 and this is R2, the currents are now going to not be the same. They're going to be proportional by Ohm's law, E equals IR again. And the currents are going to split. But what that means is that, most importantly, if I were now to take this out, what would happen to this R2?
We don't care.
We don't care. It would still keep working. This is how your house is wired.
Yeah.
And why is that important?
Redundancy.
Well, and that, if let's say somebody unscrews a light bulb,
Your
it
whole house
doesn't,
doesn't go
it
down.
doesn't turn off all the lights in your house. The other one is that each one of these devices, which is now wired into your house like this, operates the way that it's supposed to using full voltage. And this is known as parallel wiring. So the other one was called series. This is known as parallel. Okay, so now we're going to do some basic Ohm's law calculations. So we're going to have a battery, and we're going to make it a 10-volt battery because 10 is a really easy number to work with. And then we're going to have a resistor, which is going to be 10 ohms. This is our E, this is our R, and this is our unknown I. So to solve this, 300. Oops, sorry, wrong thing. Just thinking about the wrong thing. E, I, R, like that. Here's our circle. The thing we don't know is our I. So we're going to cross the I out. So we have I is equal to E divided by R. And what's our E in volts?
1.
10 volts.
Yeah.
And what's our resistance?
10.
And notice it's volts per ohms. That's known as an amp. And it's 1 ampere. So our current is 1 ampere. So how many electrons, and actually I was having a discussion with somebody this past week, how many electrons flowing past a point, that is a definition of a current, how many electrons flowing past a point is an amp? Can anybody grasp how many electrons that is really?
No.
A lot.
A lot.
Yeah, because electrons are really, really small. They don't have a very big charge. So this is 1 amp. It's, if I were to draw it, it'd be 6.24 times 1 with 18 zeros after it per second. That's a lot of electrons. That is why we use this thing called an amp, because that is an almost inconceivable number to deal with. So we call that 1 amp or 1 ampere. Okay, so now what we're going to do is, now that we've established that we can use Ohm's law, we're going to add another law. And it's also called Ohm's law.
Mhm.
We're going to make it a different color. P equals I times E. Okay. The bottom one is Ohm's law. E, I, R. Here's our circle. Here's another one, PIE, like pieces of a pie, where I is our current and E is our voltage and P is power.
Power.
Measured in watts. Okay, so due to conservation of energy, a power is defined as 1 joule, which is a unit of energy, per second being dissipated. A joule is the fundamental unit of energy in the meters, kilograms, MKS seconds units. Okay, we measure it in watts, named after James Watt, who was a scientist in the 1800s, worked on steam engines and things like that. Power conservation is very important. So, well, okay, so let's say what is right now the energy being delivered, or the power being delivered by the battery. Well, what's the voltage of the battery?
10.
10 volts. Okay, how much current is being delivered by the battery?
1 amp.
1 amp.
1 amp. Okay, so we don't know our power. Well, I times E.
10.
Yep, it'd be 1 amp.
It's 10
times
watts.
10 volts is 10 watts. Okay, if the battery is delivering 10 watts of power, how much is the resistor getting rid of? It is the only thing in the circuit that is getting rid of power. What do you think? If 10 watts is being supplied by the battery, how much is
10
being
watts.
gotten rid of by the resistor? It's 10 watts. And how does it come out of here?
Heat.
Comes out in the form of heat. If we were to change that to a resistor that produced 100 watts, that would be a heater. Even 10 watts is a heater if you have an easy bake oven. I believe that was a 40-watt light bulb, and if you maintain all that heat, you can actually cook a cake with it. So a resistor turns energy into heat. Okay, so now, once we've established the other form of Ohm's law, we can say, okay, well, if we have let's say a 10 ohm resistor, just like the circuit that we drew, and we're going to have a problem with this circuit. Something bad happens. So for the time being, we're going to be pulling 1 amp. So if we were building the circuit the way that it made sense to do, we would have a current of 1 amp. Would we use a really big piece of wire for that? What do you think?
Yeah.
No,
Yeah,
it's 1 amp is pretty small, realistically. So why would we use an expensive piece of wire to carry that? Right? It's a pretty tiny wire, and yeah, there's not really any harm in doing so. But now let's say that somebody were to come along and accidentally do this. How much is our resistance now?
0.
Pretty close to 0. Now the wire is the source of the resistance. This is known as a short circuit. Okay, so now if we still have a 10-volt battery, do we still have 1 amp flowing?
Yes.
No.
Nope. So let's say that our new circuit resistance is 0.1 amps. Or sorry, 0.1 ohms. That's our new resistance. 0.1 ohms. Okay, so we use Ohm's law again, figure out our current. E, I, R. Well, we don't know our current. E divided by R is equal to 10 divided by 0.1, which is
100.
100 amps. Okay. If the battery is big enough to supply that, How much power will the battery be supplying?
Supplying.
1,000.
Yep. Because
100.
okay, we've got to do something about all the feedback. Okay. So now we have another equation. Yep, P is equal to I times E. P I E. And we now have, we don't know our power. We have I, which is 100 amps, times E, which is 10, which is, as you said, 1,000 watts. Okay, so if the battery is supplying 1,000 watts, what is the resistor doing with those 1,000 watts?
Getting hot.
Getting hot. Okay, and what if that resistor is our wire?
Melting.
It's melting. Yeah. Or getting really hot and setting something on fire. So this is known as a short circuit, and it is potentially a very dangerous thing. So what we do is, to protect ourselves in cases like this, we insert a sacrificial device in the circuit right here, which intentionally melts internally. It intentionally disappears if the current gets too high and opens the circuit. So when that happens, what we end up with is, if the current gets too high for a short period of time, it will then turn into this circuit. And that has a name.
Open circuit.
That is now an open circuit. That's right. That is an open circuit, and this device that did that is known as a fuse. It could also be a circuit breaker. Fuses typically act faster than a circuit breaker. And the main goal of a circuit breaker or fuse is to prevent situations where there is too much current and thus too much power being dissipated, and intentionally sacrifice themselves to prevent your house from burning down, or to prevent damage due to some kind of fire. That is the same reason why, if, let's say, you have a circuit breaker in your house that keeps tripping, you keep resetting it and it keeps tripping, what's the problem?
Short circuit.
Yeah, you probably have a short circuit somewhere that's causing you some serious problems. Now, you might want to keep resetting it because it's annoying, but really what you should do is go figure out what's actually wrong and go diagnose it. Okay. Any questions about that before we move on? No? Okay. So now we're going to add another kind of thing. Instead of a plain old battery, we're going to change the battery a little bit, and we're going to make it look like that. This is a different kind of battery, isn't it? The other battery looked a lot like that, and it had a plus and a minus. Well, this...
Alternating current.
Yes. So if we were to map the battery current that looks like this, what would the battery voltage look like over time? If this were a 9-volt battery, this would be at 9 volts, and it would stay at 9 volts forever. But now let us say that instead of this 9-volt battery, we have a 9-volt AC power supply. This is alternating current. This, which you get out of a battery, is known as direct current because it always has a voltage that causes current to flow in one direction. This other one is known as alternating current. If we were to map this one over a period of time, here's our 0 point, it would look like this. Huh. Anyone recognize what that kind of looks like again?
Sine wave.
That looks like a sine wave, doesn't it? Yeah, I'm going to draw it again because I didn't like the way that one looked. There we go. So this is now our AC. Alternating current. Well, what do you notice about it? If our 0 point is right here, what do you notice about our alternating current? Some interesting things about it.
Goes below 0.
It goes
Both
below 0.
positive and negative.
And it's positive sometimes, right? So sometimes it's plus and sometimes it's minus. So what if we looked at the way the current flowed through this? If it was positive for a period like that, the current would flow that way. What happens when it goes back the other way and changes? The positive and negative signs change. What happens to the current?
Goes the opposite way.
Goes the other way. So, is it possible that the electrons in this area are never actually getting to the resistor?
Potentially.
Is that possible that they're never actually making it there?
No.
Yeah. What's really happening is that each electron, as it moves, is moving the next electron in the chain and moving the next electron. And if it's happening fast enough, the electrons that are doing all the work over here in that resistor and making heat and stuff, making a current, are local to that resistor and have absolutely nothing to do with the electrons that are being moved by the battery. But they're connected through the wire. So when you buy power from your power company, you're not actually buying electrons. What are you actually buying?
Movement.
You're buying the ability to move the electrons in your own home. Exactly.
The electron's already in the wire.
That's right. You already have the electrons. You're just buying the energy needed to move them back and forth. Okay, so AC versus DC. So it is time to bring on the next thing, which is the fact that, and I promise we're going to get back to antennas very, very soon. So what we're going to do now is we're going to draw our AC circuit. And here's our resistor. And what does our voltage coming out of our AC circuit look like again? What picture?
Sine wave.
Sine wave. Okay. So now, let's say that this is 120 volts AC. Where do we find 120 volts AC?
In your house.
In your house, okay? Now, this also has a frequency because it's a sine wave. In the United States, this is 60 hertz. This is actually going to be really important too when we start to talk about antennas and grounding and RF versus power grounding. So this is 120 volts at 60 hertz, which means that 60 times per second it makes that entire wave, which means it goes from 0 to plus to 0 to minus to 0 again. 60 times every second. So this is actually about 16.67 milliseconds. That's the amount of time needed to make one wave. But importantly to this, it switches back and forth constantly. So here's the question. We decided that P is equal to I times E. Does everyone agree with that?
Yeah.
That was from Ohm's law. Okay. Well, during this time, if we have a plus voltage, which way does the current go? It goes like that, right?
Correct.
If we draw the other half and we make it this color, which way does the current go?
The opposite direction.
The opposite way. So the question is, when we get to these different sections, are we still delivering power to that resistor?
Yes.
Yes. How about when we're at 0?
No.
No. When we're at our zeros, we are not delivering any power. And because what is the other part of Ohm's law? E equals I times R. If the voltage E continually changes, what happens to the current?
It does the same.
it does the same thing. It goes up proportionally. So it turns out that if we combine these two equations, what we find is P is equal to V squared over R, or P is equal to I squared times R. Okay. So if our voltage is going up and it gets to a peak, where are we getting our peak power? Up here at the top and all the way down at the bottom. And how much is being delivered at the 0 points?
None.
Zero.
0. So actually what we're getting is power that instead of looking like that, our power looks like this. Where it goes to 0 and then goes up to peak and goes to 0 and goes up to peak and goes to 0 and goes up to peak over and over and over and over. Okay, so now let's take a look at the simpler case where we have just
Excuse me, do
a
you mean
battery.
that's rectified?
No. Well, yes, but no. But let's take a look at this. What's the simple equation for this? If this is our battery, we'll call it letter V or E. This is R. We do our Ohm's law stuff. And what would the power look like for this? Does the battery voltage ever change?
No.
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 Eventually,
If the
it'll
battery voltage
leak.
doesn't change, does the current ever change? Well, okay, but if the battery voltage doesn't change, then the current doesn't change, and what happens to the power? What happens to the power?
Stays the same.
Doesn't change. So what we do is we can actually look at the power curve for this battery. Okay, so what we now have is a constant power. What do you think it would be possible to take a look at this bumpy curve and make it so that the average over time is exactly the same as the red
Yes.
curve?
Yes.
Sure. This has a name.
This
This is
has a
called
name.
RMS.
RMS. Root mean square.
That is root mean square. It is the voltage, the equivalent AC voltage that produces the same amount of power as a DC voltage. This is known as root mean square. So,
brings back memories.
interestingly, when you do this, when you look at the wall voltage, and it looks like this, and here's the resistor, and you're measuring the wall voltage, you will see that this is 120 volts AC. If you were to plot this on an oscilloscope, which is a device that measures voltage versus time, what you'll see is that it looks like a sine wave, like this, with a peak at 170 volts and a negative peak of negative 170 volts. And why is that?
Because it goes to 0.
Because some of the time it's at 0. So the peaks have to be big enough so that if we're calling it 120 volts, it has to be able to make as much power as a 120 volts DC voltage. In order to do that, it goes up to here and way down to here. This is what we actually
because
get.
it has to average.
Because it has to average. We go and
Yep.
we look at our voltage, and it's 120 volts AC RMS. That's what's in our wall at 60 hertz.
.707.
Yep. And it's a square root of 2. Exactly. And we could do the mathematical derivation, but I don't want to here. So, okay. So now we've done some power and we've done some resistance, and resistance is futile. Anyone? Anyone? Resistance is futile.
Borg.
The Borg. Yep. Yep. Okay. So now we're going to move on to some other interesting things. We're going to add a couple of devices because what is this thing called again?
Resistant.
The only thing we could do to make this interesting is by doing that to it. That's known as a potentiometer or a variable resistor. That arrow across it means that it is variable. This will be true everywhere throughout schematics. If you see that arrow going through something like that, that kind of means you can change it like a knob. It means that it's a variable value, which can be very useful. We use potentiometers for things like changing the output of a power supply or for changing the volume on your stereo, right? So people actually like potentiometers, but they're kind of boring. So what we're going to do is we're going to add a couple of devices. The first one, we're going to draw two parallel plates of metal. These are conductors with a space in between, and we're going to fill it with this pink stuff, which could represent air, it could represent plastic, it could be any number of different things. So it's two conductors separated by a material that is an insulator. In this particular device, this is known as a dielectric. Dielectric means it does not conduct electricity. Really, this is an insulator. This device as a whole has a name. This is called a capacitor. It has the capacity to store electric charge. The big letter C represents a capacitor, and its units of size are farads, or the letter F. The way to think about a capacitor is that we are basically putting electric charges in places where they don't really want to be. So the way to look at this is we have a battery. Which has a plus and a, now I screwed that up completely. That's when you just redraw it right from the beginning. There we go. So now here's our battery, and here's a capacitor. Again, it's just two metal plates with a gap in between. And just for consistency, I'm going to make that pink on the inside. Okay, so now once I have charged up, once I've connected this battery to this capacitor, what will move to the negative side of the capacitor out of the battery?
Nothing.
More negative.
Oh, yeah. What'll happen is you get electrons, which are negatively charged, and you'll end up with negative charges flowing out of the battery. There we go. And what will happen on the other side of the capacitor?
Positive.
You'll get positive charges, which flow over to here. And where will what are positive charges really? It's a lack of electrons. So the electrons will essentially be called home. And the electrons down on the bottom are going to be supplied to the capacitor. So while that's happening, while that is charging up, how much current flows? Actually, quite a bit, right? Because what is the definition of current?
The flow of electrons.
Yes, current is electron flow. And if you have an uncharged capacitor, what happens is it's neutral to begin with. So essentially you have this, right? Well, the battery sees, oh, well, it's neutral. I'm going to send electrons or call them back. The movement of electrons is current. So the current allows that to form. So if you were to look at that, you would say, for a short period of time, I have a lot of current. How about when the capacitor gets as full as it can. It has met its capacity. That's why capacitors are called that. It's met its capacity. What happens to any further electron movement?
Stops.
Yeah, it stops. It has they have nowhere else to go. The capacitor's then charged. How come the capacitors don't jump that gap?
Magic.
What is that gap filled with or made of?
Insulator.
It's an insulator, which doesn't allow, up to a certain point, it does not allow the electrons to make a jump. But what do they really want to do?
They want to make the jump.
They really want to make the jump. Or what they actually want to do also, if you think about it, if they're now constrained in these pieces of metal, what are they trying to do?
Get out.
They're trying to force these two pieces of metal, because you have pluses and minuses. They're trying to get them to fly together because they are attracting each other. The ability that we have now created inside here, this is what we have. This is known as an electric field.
So you make a spark gap.
Well, you hope you don't.
Kind of. Well, yeah, but I mean, you can if you're trying to.
Yeah. So
like the old telegraph machines.
Yeah. So what you've done is you've created an electric field that is attempting to pull these things together. So because you now have a field in here, you have stored energy. A capacitor stores energy in an electric field. Basically, in that gap, there is the potential.
So it's actually stored in the gap.
Well, it exists in the gap.
Side. Right.
It's essentially the energy is the desire to keep them from flying together.
Oh, okay.
It's the electrons are trying to move the stuff together, and it's resisting it. So basically, it's kind of a stable but unstable situation. So what happens if the voltage across here gets too high? Let's say that this particular material in the inside of here is rated at 30 volts, and you have a voltage of 50 volts across the capacitor.
The insulator breaks down and it jumps.
The insulator breaks down and you get a spark. Right? Yep. And you let out the magic smoke. That was an excellent answer. You let the magic smoke out of the device and it suddenly doesn't work anymore. Okay. So what you're doing with a capacitor is you're storing energy in an electric field. Okay. So now what we're going to do is do to draw another device. Well, if something stores energy in an electric field, what do you think? There's got to be something else that does. Considering we're dealing with
releases the energy.
Considering we're dealing with electromagnetics. Well, there's electro, so there must be a magnetic portion, right? There must be a magnetic analog. So what we're going to do is we're going to now draw this. But actually, what we're going to do is just draw that. All right. So this is known as an inductor. It can also be known as a coil. It uses the big letter H for henries. That's the measurement. And its symbol is the big letter L. Okay. So now, what is the difference between these two pieces of wire that I have drawn?
One is just straight short and the other has a magnetic field.
Well, the one on top is a coil. It's a coily wire.
Right.
And the one on the bottom is just a straight wire. Well, now, what if I move a current, which is just the flow of electrons, through here? What will form around this wire is a magnetic field by Lenz's law. What happens if I have a coil and I move electrons through it? I have my magnetic field that forms this way. But then inside that coil, what I end up with is I end up with magnetic field lines that sort of form this shape. This has another name. It's also known as a solenoid. So what you end up with is your magnetic field lines, instead of just going around, now form loops. Okay. Any wire that carries current can be an inductor. This is actually really important because that means if current moving through a piece of wire can make a magnetic field, what does a magnetic field generate? If a piece of wire is found inside it, it generates a current. So a current generates a magnetic field, and a magnetic field generates a current. Okay, so very importantly, what we're going to look at is a coil, which has flying around it, if you have a current flowing through it, a magnetic field. And you'll have magnetic field lines that go like this. So if I have a current flow that goes like that, it generates a magnetic field. It gets up to a certain point and it is stable. And then what? Has anyone ever taken a battery and hooked it up to a coil on a nail and used it to pick up paper clips?
Yeah.
Okay. That works, right? That's an electromagnet, right? That works great. Now, what happens if I have that magnetic field and I suddenly remove the current flow?
Drops the nails.
Yeah, but what happens to all that magnetic field energy? Energy can neither be what?
Created or
Energy can neither be created nor destroyed. It just changes form. Okay, so now I have all this magnetic field energy and it really needs to go somewhere. So, has to go somewhere. So what happens is at that point, you have all this magnetic field energy and you have this, and that magnetic field energy will attempt to dissipate itself by inducing a voltage across the coil.
through my hand when I pick it up.
Yeah. Has anybody ever seen this happen? I'll bet you see it every day. I'll bet.
Static discharge.
Yeah, I'll bet you see it every single day.
Every single day.
You can
Every
charge
single day.
Every single day.
Can you think where you might see that every single day if you drive a car?
Spark plugs.
Spark plugs, exactly. What happens is you generate a magnetic field and then you collapse the current and you force that energy to have to go somewhere. If you give it a preferable gap to jump across, aka a spark plug, it will generate a spark, which will ignite the fuel in your engine. So that's using electromagnetics to our benefit. Okay. Let's see. Next, we're going to look at another consequence of this. So what we're going to do is we're going to draw our coil and our capacitor. So now we're going to look at the capacitor first. We're going to have an AC circuit, but we're going to draw it like this. Here's our capacitor. Okay. So we're going to have a plus terminal and a minus terminal. So while that's connected, what's going to collect on the top of the capacitor? A bunch of pluses. On the bottom, we're going to have a bunch of minuses. We are going to intentionally take this battery and flip it upside down. And our plus has become our minus, and our minus has become our plus. So what happens to the charge, to the minuses that are now on the capacitor?
The pluses.
Yeah, they're going to travel this way. And what's going to happen to the pluses on the top? They travel back that way. Eventually, they travel back until there are none. And now they're going to get replaced with
The opposite.
the new charges, right? So our pluses are down here and our minuses are here. Well, okay. Then we decide, okay, well, I like where this is going. Let's switch it again. So we're going to draw our battery again like this with our new pluses and minuses. So what's going to happen to the existing pluses? They're going to come back through the wire and whoop, same thing over here. They're going to eventually dissipate like that and then be replaced with brand new charges matching the battery. Okay, the act of changing these plus and minus on the battery, that has a name. What is that? What kind of current is that? What kind of circuit?
AC.
That's AC. So if we do that fast enough, does the capacitor doesn't even have time to fully charge. While it's charging, though, it seems as though there's a lot of current flowing into it, right? While it's discharging and charging, there's actually a lot of current flow. So if we now replace this with AC, the capacitor looks like this. What is that?
Don't need one.
Short
circuit.
A short circuit.
Yeah.
In the extreme, the capacitor disappears and looks like a short circuit with AC. We can do the same thing with our inductor. And what happens with the inductor is we do this. All right, we have our pluses and minuses. We get a current flowing. We get a magnetic field that's forming that goes like this, for instance. But now we suddenly reverse this and we change our battery around so that it looks like this. Now we have pluses and minuses here, and the current is flowing this way. But there's already a magnetic field and it's going the other way, right? What has to happen to that energy?
It has to go somewhere.
It has to go somewhere. It does not like that. The inductor does not like it when you change that. You force it to change. It was perfectly happy with current flowing in one direction. Now you have to somehow absorb all that energy and dissipate it, and then get it so the current is flowing back in the other direction, so that the magnetic field can form in the other direction. Once that's in flow, everything's fine. But then what do you go and do? Because you're basically doing an AC circuit. You go and screw things up by doing what? Reversing it again. Well, if I were the inductor, I would say, I don't really like this. Why are you doing this to me? Right? You're making me have to dissipate all this energy somehow. And now I have to do it again and change the direction yet again. Ugh. What ends up happening is that the inductor basically with all this energy fights back and says, I don't want to do this at all. So if you hook up an inductor in the extreme to an AC source, what you will get is something that looks like this. And what is that?
Open circuit.
That's an open circuit. In other words, if you put AC into an inductor, what will happen in the extreme? It will not flow. This is actually really profound because there are it's not complete. It varies by the size of the inductor and the capacitor. But in the extreme, what happens is that the capacitor will pass AC and the inductor will
Not.
block it. Whereas with the inductor, if you have DC, it looks like a short circuit. So the inductor will pass DC. The capacitor, on the other hand, will not allow any current to flow. So instead of looking like an open circuit or like a short circuit, it will become an open circuit. So what does that now mean? Resistors are really what? Boring. Right? They're boring. Does a resistor matter? Does a resistor care if it's seeing AC or DC going into it? No, it just goes with the flow, quite literally. Capacitors and inductors, it makes a difference. They care. And in fact, there's another characteristic of these devices, which is called reactance, which is a big letter X. Unfortunately, it's also measured in ohms. Reactance is specifically how a device behaves when it is exposed to AC. For a capacitor, it's 1/2 pi FC with a negative sign in front. For an inductor, it's 2 pi FL. Okay, so let's see if that makes sense. Let's see if that makes sense based on what we already know. If our frequency right here, that big letter, that big curly F, which shows up in both of these, let's say that it is 0. What has a frequency of 0?
DC.
DC. That is known as DC. Okay, so what happens to our capacitor? What's 1 divided by 0?
0.
It's not 0.
Infinity.
Infinity. Yes. And we said that for DC, the capacitor is an open circuit, which is true. Okay. How about for an inductor? 2 pi times 0. What's 2 pi times 0? It's 0. Okay. Well, so far, so good. Now we're going to put infinity in there. We're going to replace that. AC, we're just going to say it's infinity for this case. So what's up top, the capacitor, what's 1 divided by infinity?
That brain hurts.
What's 1 divided by infinity is 0. And how about for the bottom one? What's 2 pi times infinity?
Mm.
2 pi times infinity is infinity. Infinity resistance is an open circuit. Infinity ohms is an open circuit. So the math works. We just showed that our formulas for reactance of these things actually make sense. But notice that's if we give it infinity. If we make it infinity frequency. But how about if the frequency is not infinity?
Bluetooth mode. AUX mode.
What happens if the frequency isn't infinity? If it's somewhere between 0 and infinity? What's going to happen to those values?
They'll change.
They're going to change. That's right. And in fact, what's really cool about this is that we can actually change them in a way that we want to. So there's XC and XL. We can actually change these in a way we want to. by changing the frequency, we can change how they behave. The other thing we can change is what if we take, for instance, a capacitor that looks like this? What does that diagonal line mean again?
Variable.
Variable. What if we take an inductor that looks like this?
Variable.
It means it's variable. We can change the value. Okay. So now, what if we do something like this and we take, notice the capacitor is negative, and we take a resistor. Okay. So let's do a resistor first. We have R1 and R2. In a resistor circuit, these add together. The total resistance is R1 and plus R2. If we were to draw that circuit differently, like this, and make it a parallel circuit, the resistance would actually be something else. It's R1, R2 over R1 plus R2. But you don't have to remember that for this class. But what's important to note is that impedances and reactances behave the same way. We add them together. So if we have this, and we have X, C, and XL, notice that the XC up here has that negative sign in front of it, and the XL has a positive sign. Could we pick these values so that those add up to 0?
Sure.
And guess what happens when they add up to 0? We get some
resonance.
We get 1 over 2 pi square root of FC or LC as the solution, and they completely cancel each other out. Well, okay, let's say we have a circuit that's built that way. And we have a mystery frequency here, and we have a capacitor and an inductor. Based on the capacitor and the inductor that we pick, what can we do with this? At one particular frequency, what will happen to this value, FR? It will go to 0, and these two devices will be replaced with a short circuit.
Okay.
For one specific frequency.
Oh.
This is known as a filter because it allows one specific frequency to get through easier than others. And this is actually known as a bandpass filter. This is, remember when we looked at all those different colors and on that frequency spectrum, and it looked kind of like this. And we said, okay, well, our eyes are really good at telling the difference between red and green and blue and stuff like that. But how do you tell radio frequencies apart? Right? That seems a lot harder, right? Well, what it takes is something very special. And we're going to go here, and we're going to make this open again. This is a filter right here. It's a digital version of the exact same thing. And what we are doing by doing this, we are changing how that filter looks at the entire world of all these different frequencies that exist, and we are selecting just that one little piece. That is the entire point of how we receive radio signals. By looking at, the entire spectrum and just selecting for one particular frequency because of capacitors and inductors. Now, again, we can do, that was digital, but if we have capacitors and inductors, we can build a circuit out of those that rejects or permits very specific frequencies to come through. which is incredibly powerful. That allows us to build things like oscillators. That allows us to, if we have a spectrum that, for instance, looks like this, where we have a whole bunch of different signals, we can build a filter using capacitors and inductors that looks like this, that allows just this particular range of frequencies to come through and takes all those other ones and gets rid of them. It's incredibly powerful tool. The other thing we can do with this is we can build our own. You know, we, as ham licensees, we have the ability to actually design and build all this stuff. So, how about a 5-minute break, everyone?
Sounds good.
Sounds good? Okay.
Hey boss, just a quick question. I have a meeting I have to jump on at 2 o'clock that goes from 2 to 3. And then I'm gonna jump back on. Is there gonna be recording available afterwards so I can fill my notes in?
He stepped away, but he said earlier that he was recording it and that he was
Oh.
gonna send us the link.
Word. Cool.
Yeah, he usually posts where you can read it the next day or whatever.
Okay. We're just getting to the point that I'm like, I don't have any experience and I'm gonna miss the most important stuff. Cool.
I think he's supposed to finish this class at 2 o'clock. 2 o'clock.
Yeah.
Oh yeah, I'm in a different time zone.
Sorry about that.
I think he posted on the private Facebook page.
Yeah, I'm gonna have to get on that. I got all this information out of 2600, so my group of nerds.
Questions before we go further? No questions yet?
Scott, are you muted?
How about now?
Scott, can you hear us?
Yep. Can you hear me?
Yes, sir. We can now.
Okay.
Yeah, I can hear you now.
Yep. Okay. Anybody have any questions before we get going?
I actually have a quick question now that you're back.
Good. Good.
Is this meeting in this? I have to step away for a meeting at 2 o'clock, but it'll be back at 3. Am I able to leave in the interim and then rejoin, or is it once I'm out?
No. Anyone
Okay.
can come in anytime.
Okay. I'll be back in an hour.
Okay.
Thank
Have
you.
fun. All right. Other questions before we get going? Okay. Here we go. Here we go. All right. So what I'm going to do is draw a very basic another circuit, which has a battery, which has, let's say, 5 volts, and this thing called a diode. A diode is a device which is made of semiconductor material. And again, this is going to have intrinsic material, or maybe not, but it's going to have P material, which has pluses in it, and N material, which has negatives in it. It's silicon with a little bit of either boron or phosphorus or some other materials, other elements that are called dopants. What they do is that they make this device into a one-way street for current flow. The band is called the cathode, if you see one. Again, this is called the cathode. And the band indicates the negative side of the diode. Again, notice we have the arrow. It looks like this. This is the schematic symbol for it. What this means is if we have a plus and a minus here, in turning it on, this will typically drop between 0.3 and 0.7 volts in order to activate. That's a forward drop, as it's called, which leaves, if we have 5 volts to start, and we, let's say, have a 0.7 volt diode, which is silicon typically, we will have 4.3 volts remaining for this resistor. So we could figure out if we have 4.3 volts, if we know what the resistor is, we can figure out what the current is. What's interesting about a diode, again, is that it only works in one direction. It has to have enough forward voltage in order for it to activate. But let's say we were now to take this and turn this the other way, where we have plus and minus. Well, a diode like this, in order to function properly, needs 0.7 volts in order to function. Well, considering that this bottom side is now the positive side, this diode will not work. And so how much current will flow if the diode doesn't work? That would be nothing. Zero. So essentially, the diode becomes a one-way street. That gives us some really, really cool powers. Here's the coolest power of the diode. Okay, what does this little thing represent again? It represents AC. Okay, so we have AC going in to this circuit. In a very, very simple circuit. So what happens when we have plus voltage? What will happen to the diode?
It'll activate.
Yep, it'll activate. Okay, so we draw the voltage right there. We will have it going like this. What happens when the voltage goes negative?
Shuts off.
It turns off. So we don't actually have anything going through. We have this. Well, does that ever go negative? It goes to 0. 0 is okay. And it never goes negative. This has a name. What did we start with?
AC,
And what did we just make from it?
DC.
We made a
Oh,
very
so it's a
ugly
converter.
we made a very ugly form of DC. We have converted AC to DC. This is known as half wave rectification. Because we have basically taken half of it, half of the wave, and done something with it. Well, okay, we now made DC. Well, as it turns out, what's another way we could clean this up? Instead of just running it through a resistor, we could clean this up by taking our old friend, the capacitor, like this. And what happens to the capacitor? When this voltage goes up, the capacitor charges up. And when it flips back around and the diode is not working, the capacitor is already charged. So the capacitor at that point will supply voltage to the resistor. So some of the time the capacitor is charging, and some of the time the capacitor is supplying the voltage. So if we were to look at that waveform, we would see something that looks a little bit better. We would see something that now looks like this. Which is somewhat filtered DC. If we now, instead of that, added
So is
something,
it just charging and discharging constantly, basically?
that's all it's doing. It's filtering the voltage. It's cleaning it up.
Okay.
We can also now add another device which looks like this. Huh, what does that look like? Looks like another diode, doesn't it?
Yeah.
Except that it's backwards.
Zener.
That's a Zener diode, which is a voltage regulating diode. These are specifically designed for a certain voltage. So let's say it was designed to allow anything above this level to pass through. There's a resistor just to protect it. What comes out the other side? You get that nice blue line. That nice blue line is pretty flat, isn't it? That is rectified and cleaned up DC. This has a name. This is a power supply. That is a basic half-wave rectified power supply. So in order to make this more efficient, another thing you can do with it is, here's your AC. You can give this current two different paths to follow. So that it goes out this way. You could also say that it goes back this way. I think I drew that wrong. Let's see. Yeah, I drew that wrong. I'll clean it up.
What would be an example of this, Scott?
So here, I'm going to draw it the right way. Instead of using one diode, you would do this. There we go. And then what you end up with is something like this. I think I drew it right this time. 4 diodes. And so what you end up with is when the voltage is going one direction, you have a pair of diodes that are operating, which are the green ones. And the other half of the time, when the voltage is looking like this, you can follow your way around and find that it goes through everything and goes back the other way. And this is actually known as a full wave rectified. Power supply. This actually has a name. What would it be an everyday example of this?
Alternator on the car.
Yeah, alternator on your car. How about something that looks like this that your cell phone plugs into or your computer plugs into? That's a diode bridge. And this is typically what you'll find.
I have a question.
Uh-huh.
Will that rectifier on the bottom be redundant?
Which one? You still need all four.
Diode?
If it's full wave rectified, you need 4 diodes.
Yeah, but the electricity goes from the negative and that can never get to that lower diode.
It will, because if we're doing this direction, it will go like this way, this way, this way, this way, this way, and back to the battery.
Oh.
It changes direction of flow. If it goes the other way, the path goes like this way, this way, this way. It gets blocked, then it goes through the load and has to come back this way.
Okay.
So basically, those 4 diodes, there are actually only 2 of them operating at any time.
So what does that do? Basically eliminate surge or interference?
No, it's just more. It's more efficient.
More efficient.
Because you're rectifying. You're operating for the entire wave as opposed to just half of it.
No, okay, gotcha.
So you can make more power out of it. And again, what I didn't draw on here. What I didn't draw is a big filter capacitor. There's going to be a big filter
But
capacitor.
wouldn't that all those diode give a lot of voltage drop? You say it's more efficient, but
Well, it's okay. Okay, somebody's got a lot of feedback. Let's there is more voltage drop because you have 2 diodes instead of 1 that are in line at any time. But the way you would but you're using the entire waveform. So instead, if you're looking at this, you're using the entire waveform as opposed to just the top parts. And
okay, that makes sense.
So here's the other part of it that is important. That now we need to make a voltage that's of some use to us, right? So let's say we have 120 volts coming in from the wall. 120 volts. We want to power a cell phone charger. Okay. 120 volts is not going to do us much good, right? So what we do is we do this. We have a coil. What does a coil generate? What does an inductor generate?
Electromagnetism.
Magnetic field.
Magnetic field.
Okay. So then we take the magnetic field and do our best to constrain it inside an iron core or steel. Those are ferromagnetic materials, which are very conducive to carrying magnetic fields. So what we do is we constrain it, we wrap our wire around it, and we end up with a turns ratio which is
transformer.
The number of times that the coil is wrapped around the iron core. And we have a ratio of the number of times that it is wrapped around. Turns out that if we have V1 and V2, V1 over V2 is equal to N1 over N2. So it's proportional. It has to do with magnetic flux lines and cool stuff like that. So if we have a turn ratio of 10 to 1, so let's say this is 120 turns of wrapping around, and this is 12 turns, we have a 10 to 1 ratio. Our output would be 12 volts AC, which is pretty cool because we started with 120 volts AC. And where's the actual electrical connection between these two?
There is none.
There is none. That's right. It's magnetically coupled. This is known as a transformer. This is how we step down power from the power lines down to a voltage that we can use inside our homes. And this is also how we step down and up power to be used in different places. So 12 volts AC. We now have 12 volts AC coming into here. We have our bridge rectifier that looks like this. Going through our capacitor and our Zener diode. Going to this resistor. That resistor is our cell phone that's being charged. And all of a sudden, we have a circuit that is now working. And we use this diode bridge to convert the AC to DC, the ugly DC. The capacitor filters it. The Zener diode trims off the peaks. And then we use that to power our cell phone. And that's what we have when we do our computer power supply or whatever you may have. It's a basic DC power supply. Yes.
How are we able to use the coil on a AC circuit for the transformer?
Ah, yes. Okay. So, well, that is a really good question. Okay. So here's that AC again, and here's our coil. And the impedance or reactance is 2 pi FL. Well, again, for infinity, for a frequency of infinity, XL is infinity. For frequency of 0, XL is 0. But in between, it's not. So it actually works somewhere in between. You can, if you have a stout enough circuit, you can stuff energy into it and it's okay.
That makes more sense.
Yeah. But that's why, it generates a changing magnetic field. So yeah, because we're not talking about the extremes. In the extremes, yes, it behaves in an extreme fashion. But in between, it doesn't, which is what gives us the ability to do tuned circuits. And yes, actually, this actually is a tuned circuit. It's, you have to pick your sizes and things like that. The other thing is with a transformers, because we did this, and let's say we had a 10-to-1 ratio, if we had 120 volts over here and 12 volts over here, and we were using 1 amp over here, how much do you think we'd be using over on the other side? By Ohm's law, power is I times E. Everyone remember that? That'd be 12 watts. And since power and energy can neither be created nor destroyed, how much current are we actually delivering on the other side? Somebody said it, 1/10 of an amp. This is why we deliver power to our homes at very high current or very high voltage and very low current. Because the other part of Ohm's law is that the lower the current, the lower the voltage drop, the lower the heating and stuff. So that's why your power lines out on the street are 12,000 volts. That's why power lines from the power plant are almost 1,000,000 volts. Because you can deliver it at very low current, and the higher the current, the bigger the wire you need, the heavier it is, the more expensive it is. So if you can jack the voltage way, way up, you don't have to waste energy. You don't have to waste energy. You don't have to waste money, and you don't have to put up power lines that are going to sag and then crash to the ground. What's significant about this is that if we were to look at the apparent resistance and say, okay, if we're drawing 12 volts at 1 amp, okay, Ohm's law again, E equals I times R. We don't know our resistance. R is equal to E divided by I. is equal to 12 ohms. We're going to do the same thing on the left side. R is equal to E divided by I is equal to 120 divided by 0.01. Or sorry, 0.1. Uh-oh. What do we get? What's 120 divided by a tenth? 1200 ohms. We have 12 ohms over here, and it looks like 1200 ohms over here. So a transformer can also be used to transform current, to transform resistances and impedances, which is actually kind of cool. Some might say magic. Okay. Another way to use these things to our benefit is, let's say we have something that looks like this. Anybody know what that thing is?
LED.
That is a light emitting diode. Well, now you know what an LED is. A light emitting diode. Instead of just turning on when you have a voltage that turns it on and you get current across it, its chemistry is such that it emits light from the junction. Depending on the materials that we use for that, you can change the color. You can make blue, you can make red, you can make green, you can make orange. It all depends on the materials being used. And it's a very pure light as well. Okay, so that's an LED. Another one that you might find. What's that?
Switch.
That's a switch. What's the purpose of a switch?
Open
On
or
and
break
off.
the circuit.
That's right. Okay, so this is a single pole switch.
Single throw.
This is a single pole, single throw, because it can only be thrown one way. Single pole because there's only one circuit. How about if I built it like this and I put two things in parallel operated by a single operating button? That would no longer be a single pole. Yep, that would be a single pole, or sorry, double pole, single throw when you look at your switches. Now, if I built it so that I actually had another circuit that went this way, like that, I could choose two different things. Each of those poles could now be thrown in two different directions. So that would be a double pole, double throw switch. When you go to replace light switches in your house, things like that, it's important to know which is which. Okay, other ones. Okay, everybody, what is this?
Switch.
That's a switch. Okay. What if I did this?
Relay.
This is known as a relay.
Solenoid.
That's a solenoid controlled relay because this is actually got a magnetic piece on it. It pulls it down and closes the circuit. It's a magnetically operated switch. Okay. Let's see. Practical uses for circuits. Oh, this is a good one. We haven't done this one yet. This is another thing that has to get covered. Anybody know what this is?
Transistor?
That is a transistor. Okay. A transistor is a very special kind of device. It is a three-terminal device as opposed to two. You'll remember that a diode looks like this. Internally, it looks like that. A transistor looks like that. So it's like kind of two diodes back to back. And in fact, the way that it's built is that you have, in this particular case, NPN, NPN, three wires. This is called the base. This is, in this case, the base, collector, and emitter. And the whole point of a transistor is that because if we're going to look at just this part of it right here, we're going to erase that. We're going to look at 1/2 of this. What is that? That has a name.
Diode.
That's a diode. Okay. But this is a diode that's connected to something on the back side, which is this path. Which is a connection from the collector to the emitter port. The whole purpose of a transistor is to take a current that flows when you forward bias this junction and generate a large multiple of it flowing in this direction. So that if I have a separate power supply right here, when I have a small current over here, when I have a small current from the base to the emitter, I get a very big current from the collector to the emitter. Ideally, this is a linear function, which means that for every 1 unit I have over here, I may get 100 units over here. If I have 2 units over here, how many units will I get on the other side?
Okay, 200.
200. If I have 3 units over here,
300.
okay. That's known as the beta of a transistor, which is the multiplication factor. In this case, the beta is 100. If I have 4 units over here,
400.
400 on the other side. Okay, at some point, it runs out of the ability to even function properly. So that may be if I get 6 over here, I get 400. If I have 8 here, I still get 400. This right here is known as saturation. Like, I've gotten too much information and I can't take any more today. You're saturated. I'm sorry, that may be true, but
That's
so
true.
this is known as the saturation point, where I just can't absorb anymore. Now, on the other end, you might get down to 0.5 and you get 0. That's not linear anymore, is it?
Mm-hmm.
For every 1, you got an extra 100. Well, this is known as cutoff, when it just doesn't function anymore. So this range is known as linear, where it is linear, and too low is cutoff and too high is the saturation point. So
I have a quick question.
yes.
I don't remember. It's been so long, but what in that particular example, what would be the difference of flow or whatever for a PNP or an NPN?
So that's an NPN, and a PNP would look like this. So the current flow, instead of this way and this way, for a PNP, it's that way and that way. And you have to wire up the NPN is a lot more intuitive. That's why I think it's probably easier to make also.
Thank you.
Okay, so this is again an NPN transistor, and in particular, it's known as a bipolar junction transistor. Or BJT. That's 3 terminals, collector, base, and emitter. A transistor has 2 functions. Okay, so I'm going to draw a curve, and if this thing would stop falling, there, I'm going to draw a curve. representing the input output. Okay, so here's our input and here's our output. So at some point, I can put in input, but nothing happens to the output. But then it goes like this, and then I get so high that it can't put anything else out. Those ranges, again, are cutoff and saturation and linear range. Okay, if, let's say, I am trying to operate a computer. Does everyone know that their computer and their cell phone and everything that they're using are full of transistors? Like billions of transistors? Right? They were invented in 1947, right? They've been around for a very long time. But it's only been, I don't know, 50, 60 years since they could be miniaturized, and with laser lithography, they can be put, a billion of them on a chip the size of my thumbnail. So this is essentially what transistors do. They can operate in one of three ranges based on how they are operated. So if I am building a computer where all I have are zeros and ones, do I care about the stuff in between? Would the value 0.2 mean anything useful to me at all?
No, because you don't care about 0 and 1.
You want it to be 0 or 1. So when you're operating a digital computer with zeros and ones, zeros are in cutoff, ones are in saturation. You drive them as full to the end as you can. But if you're trying to build an amplifier where you're amplifying an analog voice, for instance, analog voice, you want it to operate in this linear range, because what happens if it's not linear? If I talk like this, or I talk like this, or I talk like this, it's supposed to get proportionally louder. What happens if it's not proportional? What does that sound like?
It's distorted.
It's distorted. That's right. So you have distortion. So analog circuits, you can use a transistor in the linear range. For digital circuits, you usually use it in cutoff and saturation. And as it turns out, transistors that look like the one that we did on the left are great, but they're not all that efficient. So you use them for very specific things. And for small circuits, small levels of power, they're also not easy to make on an integrated circuit, which is a circuit that has like a billion transistors on it. So instead, we do this. We build a transistor that looks like that. So we have three terminals. We have a gate and a drain and a source. And when we get a voltage that occurs right here, that changes the amount of current that can flow this way. This is known as a field effect transistor. And you may have seen the word FET. They're used in power transistors, they're used in amplifiers, they're used in a whole bunch of different things. And what does that thing on the left look like to you?
Capacitor.
That looks like a capacitor. Yeah. And what's inside a capacitor?
Dielectric.
How does a capacitor store energy?
Insulator.
Magnetic field.
An electric field. And that's why this is known as a field effect transistor. By putting a voltage on this one side of the capacitor, on the left, that changes what happens on the other side. By putting negatives over here, that forces positives to be on the other side. Depending on how you bias the voltage on the other side, that determines what current's going to flow. So it works across that gap. And how much current actually flows in the capacitor across the gap?
None.
Is there There's none. That's right. These are very, very efficient because they work on electric fields and not on current. That's why we build our chips that are the size of my thumbnail with 1 billion transistors on it. We're able to actually make them using field effect transistors and get away with it. That's why your computer doesn't generate, that's why it doesn't consume and generate 1,000 watts of heat. Okay. All right. Y'all ready for the next thing? There is a next thing. Okay, before we do that, does anybody have questions? And it's okay to say, oh my God, I don't understand anything. I don't know if I can fix it, but I can try.
Opinion about my fingernails, but I want to point out the issue I encountered playing with old Heath kits.
Uh-huh.
In the Heath kits built in the 60s and before, they had the diodes in one way, and in the 70s, they reversed it the other way around.
Ooh, okay. That I
Don't
don't
go in
know.
the same way, but they're logically backwards.
I'm sure there was a reason for it, but I don't know what that was. But if you send me the schematic, I might be able to figure it out.
Okay, I'll send you two in a bit.
Okay.
I have a question or concern.
Yes.
So
a concern. Uh-oh.
I've been trying to learn and get my ham radio license for a few years, but I always get stuck at this point. Should I be learning and understanding electricity before I try to even get a ham radio license, or can I just take the test and try to learn all that stuff later? Because I don't understand anything about electricity. It's Greek to me, and I'm learning it, but it's completely unfamiliar to me.
Okay. This is a good time to segue into that thought. So, all right, there's really two things. There's really two parts to this whole process. One is learning everything there is to know, right? Okay, so for a little background, I have an electrical engineering degree. I have a master's in electrical engineering. I've been doing this for 40 years as a ham. And I work in the electrical field. I build electrical equipment. So what I'm doing is I'm giving you a kind of a light version of all the electrical theory that I've had to know, that I've learned over the years, that hopefully, if a little bit gets in and you remember something like a couple of snippets that are really important, it will help you it'll help you in the future. Fundamentally, you have to take a test, right? Right? You've got to take a test.
Right.
I can't help you study for the test per se. My hope is that some of this stuff that we're doing will make what you end up studying for on the test make more sense. Because all of the questions, right? All the stuff I'm going through is material that is covered on the technician exam, or a lot of it. Right? It's basic electrical theory. It's how antennas work. It's why the spectrum is what it is. So when you actually look at the actual exam, all the questions are there, all the answers are there. You really just have to go through, and hopefully what comes out of it is that it is easier for you to study for and do well, because you have some background. Ultimately, ham radio is an experimenter's hobby. It has lots of practical aspects too. I mean, the whole emergency communications thing is incredibly important. What makes it different is that in the process of getting a license, you have all these, all these, like, they're not really superpowers, but all these privileges that come along with it. That, okay, let's say you buy an FRS radio, right? Does anyone have an FRS radio? I have several.
Yeah.
Or GMRS? Okay.
I do.
They are channelized. You can only operate on certain channels because that's the rules. You're only allowed to operate on certain channels. Some things you can build your own antennas, some things you can't. And for other services, you get a certain amount of power and the antenna can't be removed. We have like virtually no restrictions. right? This is like this is kind of like the super user version of the radio frequency experimenter's toolbox, whether you decide to use it or not. And most of that learning comes into, most of that learning comes into the fact that it's going to make your studying a lot easier, but you're also going to get to the point where, okay, if you need to, you can build an antenna and you will know how to build an antenna. You will know how to calculate how long to make it. You will understand power consumption. You'll understand power output. You'll understand efficiency. You'll understand systems where you have a certain amount of RF energy that's going out and, oh, it's not working well enough. Why isn't it working well enough? Because you don't have enough gain in your system to make it work. Your communications channel can't work that way, the way you have it built. How do you fix it? Somebody, I just saw somebody asked, why if we don't plan to use, why if we don't plan to use it, we need to study all this. It's like if you're given the ability to drive a car, right? Let's say you pass your driver's license. Well, okay, I never planned to drive on the highway. Well, your driver's license permits you to do so, right? There's a certain basic understanding that you have to have to be given the privileges that we have.
Right, but what I was basically asking is, for example, with your example of the driver's license, when you go for a driver's license, you don't need to learn how to deal with every last part of your car. You don't have to learn how to take apart your engine, put it back together, how your engine works.
True.
My question was, if we're not building our own system, we're not building our own antennas, we're using whatever we got, or we're purchasing antennas, what's the actual need for this part? Wouldn't that be more of a, I guess you can consider it a different tier. Why do they lump it into the first tier?
The easiest way I can explain it is, do you agree that okay, so true or false? This is our legal power limit on most bands. All right? That is our legal power limit. All right, 1500 watts RF output. True or false? I can build or modify a dish that I have designed myself or gone and repurposed from somewhere where I have a dish that is 26 feet across. True or false? If I build a really big tower for it, really big support.
True.
True. Okay. So if I go through the process and figure this out, and I modify a 26-foot dish, which a technician license allows you to do, and I go through the calculations and find that this antenna gives me a gain of 30 decibels, which it can. 30 decibels, which we're going to cover right after this, is 10 times 10 times 10, because it's 10 to the third power, is a gain of 1,000 times. My actual RF power output is 1,500 watts. And you have 1,000 times gain in the forward direction. What is your effective radiated power in that direction?
Oh.
Big number.
How many watts? What's the power? 1.5 megawatts. 1.5 megawatts. This is legal. We are allowed to do this. You are allowed to do this with a technician class license. And to be fair, you don't have to take a class. You don't. You can go and just grab the book. I mean, that's how I studied it in the first place when I was a kid. I went and I didn't learn this stuff until I really got further into it. But what I was hoping, what I hope is the same way that I wish that I wish that somebody had been around to teach me something like this when I was learning, because then I wouldn't have had to learn it all the hard way.
Could I interject?
You know what I mean?
Well, I'll just say an answer to my question, and I think you answered, which is basically, I can learn enough of this to get by on the test, but if I really want to do more with it, then try to understand all this, and maybe I can ask you later for some resources for learning electricity on a
Absolutely.
deeper level. Okay, thank
Absolutely.
Yeah, yeah. It's I can only tell you from my personal perspective, when you use the analogy of driving a car, you get a license that can drive either an automatic or a standard,
Correct.
but you may never have touched the standard, and
Right.
that's not working on your engine. That's just the vehicle itself.
Mm-hmm.
And I know lots of hams that they buy radios, they buy their antennas, but when you want to specifically work 20 meters using a wire antenna doing POTA, parks on the air,
Mm-hmm.
you may need to do that yourself.
Yep. Well, and in case of an emergency, part of having a license is knowing how to make this stuff work beyond just being an appliance operator. You can survive just fine as an appliance operator, but you really don't show the true value of it until you get to the point where you're trying something more.
No.
So,
Hey, Scott.
yeah.
Just Kevin. Hey, I was thinking the same thing that young lady asked, and I had taken a couple sample tests. My dad was a ham and built his own radios and talked all over the world when I was a kid. So I understand a lot of that, and he did a lot of that. He built his own radios and stuff. But taking a sample test, I scored 50% on my first test. When I went through I went through the study guide you gave us, and I didn't have a clue. It's all Greek, a foreign language. But I think this is high level, but there's a lot of things that you gave us today, these samples and these circles and that kind of stuff, that if we just remember those are a lot easier than trying to go through this book and figure out what this equals this and that equals that. Those circles, and those are little cheat sheets. You memorize those, you sit down to take the test. I mean, it's going to make it so much easier. So way above my pay grade today. But I see it, having taken the samples, that it's very beneficial. So I just wanted to share that with you.
Well, and the other thing is that if you look at the kind of stuff that we are permitted to do, right? Other services, for instance, if we look at, okay, so let's look at our fundamental frequency that we're operating on. And here's our fundamental frequency. You're allowed to build your own stuff, right? Doesn't mean you ever will, but it does mean that you are allowed to. And if the license permits you to, you have to at least show a little bit of understanding that you understand it. So let's say this is our fundamental frequency. If you look at your spectrum analysis, your spectral analysis of your transmitter, and you find that every one of these is at least minus 50 decibels down from the fundamental, then your transmitter is legal, right? But because we are allowed to build our own stuff, we have to understand at least what this stuff means. It doesn't mean you're going to be tested on it. It doesn't mean you're going to use it every day, but there is a fundamental understanding. And again, remember, the FCC gives us the access to all of these frequencies with the understanding that we know how to use them. One of the things that can happen is that, let me stop share. One of the things that can happen is, okay, you buy a transmitter, it's probably been vetted and designed by somebody who knew what they were doing. That's probably true, right? but it doesn't guarantee it. But it's probably true. Let's say that you take a transmitter, which you're allowed to do, and build it yourself. There are guidelines for what makes a legal transmitter. You're allowed to do this. You're allowed to build your own stuff. You're allowed to modify existing equipment. You can take a Wi-Fi, and to Scott's point, you're allowed to take a Ubiquity. Has anyone ever heard of a Ubiquity router?
No.
Yes.
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 Okay. You can take you can take a Ubiquity Wi-Fi router. You can jack up the power. You can run it through an amplifier. You can change the frequency that it's on and make it into a ham transceiver. Hook it up to a 30 decibel gain dish and use it for a point-to-point mesh network that will cover a distance of 30 miles from mountaintop to mountaintop at an insane data rate. Right? That's known as mesh networking. We can do that. Now, the thing that we have to know
Could you
is
repeat that process one more time? That's fantastic.
Yeah, it's basically mesh networking. We can reprogram an existing router, change its frequency if necessary, so that it's on it's on the adjacent ham band to the Wi-Fi, increase its power output, or run it through an amplifier and hook it up to any antenna we want, and run, running like from point to point, from mountaintop to mountaintop, and run really, really high data rates. Because it's essentially it's a boosted Wi-Fi system. That's part of what we call it's a mesh network. There are local versions, there are far away versions. We use it for emergency data comms. The important part to note about that is that when you do that stuff, how do you guarantee that your spectral emissions are not going to fall on air traffic control?
Right.
How do you know? Unless you know what to look for, you will never know unless the FCC comes and the FAA come knocking on your door, and you don't want that. So, in other words, they don't care, and I don't care if you never use it. Right? That's totally up to you what you choose to do with your license, which is the power of having this license. It is totally up to you. Which is what makes this like one of the greatest hobbies. You can go anywhere you want with it. You want to go into long distance communications, you want to go into antenna design, you want to go whole hog into emergency communications and building an emergency response trailer. You can do anything you want. There's many, many, many different ways to go. And this is a basic license that, number one, assures, hopefully, that you don't interfere with anyone and you don't kill yourself and you don't kill anyone else. How's that?
Yeah, Scott, I think I was just going to jump in, but you were faster than me. That's one of the things. There's a lot of power in these radios, but a lot of power that can kill you, a lot of power to reach different area of the world. And so you have to know how to use that power responsibly.
Mm-hmm. Other questions? And I don't mind talking about this. This is this is good discussion.
Good discussion.
Oh, and you get a cool call sign from the FCC.
And you can get your own call sign. That's right. And the other thing is that the responsibility of having a call sign, you are licensed just like a TV or radio station. Your license is not like a miniature license. That also means that the fines that you are eligible to get are similar to what a TV or commercial radio station is able to get. I mean, this is a real thing. It is a real license.
Scott, I'd like to just interject too that historically, the reason why all this technical information was required was because back in the earlier days, ham radio started back in about approximately World War I, but over the decades, it was really there was no commercial equipment available to ham radio operators at all. Everybody had to build their own stuff, so you had to understand the circuitry. So historically, that's why all that stuff is in there. And over the years, they pulled a lot of that out because I have books from the 60s for novice class and general class stuff. And believe me, you did have to know how to take a radio apart and put it back together again in order to understand that material. So that's well, a lot of it is kind of legacy.
What I have found, being a fairly new technician licensee in the last couple of years, retaking this class again and hearing the information, I'm having a whole lot of aha moments. That's what that means. So it's continuous learning. Don't, just because you have your license, don't stop. Keep on learning. And if it means repeating a couple of classes with a great instructor, then you just learn that much more.
And go join your local club and do stuff. You know, do an antenna build. Somebody's putting up a tower, someone's putting an antenna up on the tower. Go figure out how to do it. Be a part of it. That's you know, we learn a lot by doing. All right, let's see. Moving back, we are into let's see, propagation and antennas. This is actually my favorite part. Yeah, it's up there. Okay, so fundamentally, here's an electromagnetic wave. There's a wave. Which direction does it travel? It travels in one direction. Light waves don't like to bend unless there's something that bends it, right? So light waves travel in straight lines. Radio waves largely travel in straight lines. So that means if I have somebody here and somebody here, which way is that radio wave going to travel?
A to B.
Whichever way you push it.
Of sight. The only way to get it from point A to point B is line of sight, unless there's something in between. Right? Radio waves are the same as light. Light travels in line of sight, which means if it's not line of sight, it's going to be hitting something else and going to be distorted somehow. Doesn't mean it's not going to work, but that's what will happen. Okay, so radio waves travel in line of sight. Very important to remember. Okay, so now, once we have established that radio waves travel in line of sight, there is the ability for us to, for instance, look at the Earth as if you're not a flat earther, don't believe that you believe that the Earth is round, and we have a problem, which is the fact that somebody over here and somebody over here are not within line of sight because the Earth is curved. Right? That signal would have to go through solid rock to get from point to point. Well, that doesn't really work. So we rely on something else in order to do this. Okay, well, let's say that we're flying up here as an astronaut on the space station. Well, okay, that is line of sight. So in order to do that, we would pick a frequency that passes through our atmosphere as if it's not even there. And we would be able to talk from the ground to a satellite. I've done this. I've talked to an astronaut on the ISS. It was really cool. I just used a 3-element beam on the back porch of my house. It was awesome. First time I've ever done it. Only time I've ever done it. It lasted all of 15 seconds. So from that point, okay, well, that's one particular kind of wave to get from point to point. We could do satellite communications, which go this way, be bounced back and forth. AMs actually do that. We have a program called AMSAT, which puts up amateur satellites, Amateur Satellite Corporation, AMSAT. So these frequencies that behave that way are typically VHF, which is 30 to 300 megahertz, and UHF, which is 300 to 3000 megahertz. Those are our bands that are used for Earth to satellite stuff because, for the most part, at those frequencies, the atmosphere is transparent to radio waves. It just passes on through as if it's not even there. However, there are certain times that that's not true. On the 6-meter band, and this is a good opportunity for me to bring up this this chart. Let me go and grab it right here. This is one of the things that was sent out. Maybe. Oh, shoot. There we go. Okay. Everybody got a copy of this. This is this is our frequency allocation chart. Everybody should have a copy of this. This is very important to have. Notice that we have VHF, UHF, and we have medium MF and high frequency, medium frequency, high frequency. The 6-meter band is kind of that break point between the high frequency band and the VHF band. This is where you start to get into weird things like sporadic E-skip and stuff like that, and meteor scatter and auroral communications. Above that, you're basically mostly line of sight. Below that, you're almost exclusively not line of sight. Okay, so there's that break point at about 30 megahertz where everything goes from line of sight to not line of sight. The atmosphere is broken up into the troposphere where we live, and then the stratosphere, and there's probably another layer or two in there that I'm not thinking of. But then there's the D, E, and F1 and F2 layers. These are collectively known as the ionosphere. Because, yeah, go ahead. Okay, so these are collectively known as the ionosphere. And the reason that is what it is because the atmosphere is largely made up of oxygen, molecular oxygen, atomic oxygen, nitrogen, and diatomic nitrogen, some ozone. What happens is that the sun continually bombards the Earth with light and radio, believe it or not, as well as ultraviolet and X-rays. Well, fortunately, our atmosphere catches and traps and absorbs most of the energy from the ultraviolet and X-rays, or else our planet would basically be devoid of any life. So it's a good thing that happens. In the process of doing so, what happens is that those are very, very high energy, as you'll remember from our electromagnetic spectrum. Those have a lot of energy contained therein, those photons. And when one of those crashes into a nitrogen atom or nitrogen molecule or an oxygen molecule floating up there in the upper atmosphere, what happens is they have enough energy to completely rip an electron out of the atom. So what we end up with is free electrons and free ions. That's why it's called the ionosphere, floating around up there. This peaks during the daytime when the sun's ionization is at its peak. It also peaks during the peak of the 11-year sunspot cycle, which we are at the top of. If you remember back in May, we had a really cool aurora in a lot of places. That was a result of the fact that the sun is at its peak of solar activity, maximum level of ionizing radiation. Well, when that happens, we get high levels of radiation. We get a lot of electrons floating around over here. During the day, they keep getting made. At night, when the sun goes down, the Earth has rotated out of range. What happens is these go away, and eventually those atoms, which are missing electrons, then recombine with electrons. Density is fairly low up there. And what happens is that some of these electrons start to recombine, and our density goes down, and it changes the characteristic nature of the upper levels of the atmosphere. The essential effect of what ends up happening up there is that radio waves of different frequencies, which are able to penetrate the lower levels of the atmosphere, will have their energy absorbed and re-emitted back down toward the Earth. This is known as skip. Depending on the level of ionization that exists up there at any given time, this changes what frequencies are absorbed and what frequencies are bent. The higher the level of ionization that occurs, the higher the frequencies that get bent back down. At some point, this angle becomes steep enough that it just sort of gets bent that way and it never comes back down. This is known as the skip zone. But this is what allows us to talk over very long distances. Above a certain frequency, what ends up happening is that we send our signals up into the atmosphere and they pass right on through. And what is that useful for? Satellites. And for radio astronomy and things like that, where we want our signals to get through the atmosphere.
And Earth, Moon, Earth.
Earth, Moon, Earth. We have something called moon bounce. Yes, we do. Remember that 30 decibel dish with the 1500-watt amplifier that I drew?
Yeah.
Putting up 1.5 million watts? That would be really good for moon bounce, which is another thing that we do. You aim your antenna at the moon, bounce a signal off, and hopefully somebody else hears it and sends it back and says
Cool.
hi. Okay, so again, we get our peak degree of reflection or refraction, depending on how you look at it, during the daytime. And because during the daytime you get higher levels of ionization, you get better propagation on frequencies that require more ionization in order to work. So notice that we now look at these things in meters: 160, 30, 40, 20, 15. During the peak of the sunspot cycle at midday, 10 meters, we were listening to 10 meters just a little while ago. 10 meters has been amazing for the last year. For the 9 years prior to that, 10 meters was not even in the picture. Completely gone. Completely unusable. Because we didn't have enough ionizing radiation from the sun to make it useful. For the last year, 10 meters has been the best it's been in the last 30 years. Just the way it is. At night, these high bands, because you'll have recombination of all the ions and electrons, those bands will fade away and you'll start to get propagation into the lower frequencies. These lower frequencies should work during the day, but what happens is that the D layer, which is the bottom layer of the ionosphere, absorbs them during the daytime, which is why if you listen to, let's say, AM radio, if you've ever heard AM radio is, let's see, AM radio is up here, 300 kilohertz. Here we go. Broadcasting AM radio from 5:30 a.m. up to 17:05 a.m. You probably recognize that. Those are in kilohertz, not megahertz. It's about 1.1. It's about 1 megahertz. It is below the cutoff at which the D layer absorbs radio waves during the daytime. So what happens is that your radio waves from your distant AM stations get absorbed instead of bouncing around. At night, that layer dissipates quickly when the sun goes down, and you can hear stations from 1,000 miles away, which you've probably noticed if you listen to AM radio in your car. Okay.
I've had that before.
Yeah, AMDXing. Okay. Another thing we can do is, okay, so here's the Earth, and we have these VHF signals. VHF signals usually pass right through the atmosphere as though it's not even there. But we live in this thing called the troposphere, which is at the bottom layer of our atmosphere. And in the troposphere, we sometimes get these things called temperature inversions at a few miles up. What'll happen is you will get warm air and cold air forming layers, and you will get effectively a channel that exists and is able to, because of different indices of refraction of the air. If you've ever seen, like on a hot day, you've seen a reflection on the highway reflecting what looks like the sky. It actually is refracting the sky. It's a little temperature inversion right over the roadway. This is a similar thing, except it might be a couple of miles up. where we actually get a channel that opens up that can bounce signals back and forth through what's known as a duct over a distance of a few hundred miles. And that can exist all the way into the UHF range. I've actually heard that before. I've watched back when I was in college, I watched a TV station from 300 miles away on UHF channel 60 something, which was kind of amazing. You know, it should never work, but it did. We end up also with something called tropospheric scatter, which is signals that go up into the troposphere and bounce this way and this way. And they don't follow the normal plan. That's known as troposcatter. We also, again on 6 meters, when we had the really, really awesome aurora back in May, I had never done this before, but if this is a picture of the Earth and you have the aurora coming down over the poles like this, what happens is you have a lot of charged particles coming down over the North Pole and the South Pole. That causes us to see the aurora. Well, it turns out that aurora is generally, it's easy to think of as a whole bunch of charged particles and ionized particles. There's that word ions again. You send a signal into the aurora and it bounces back out. And I was able to I was actually able to make several contacts with people 100 miles from here by bouncing a signal up off of the area near the North Pole and hearing them as they bounce back.
Cool.
And that's known as auroral propagation. We can also, because we're looking for things that tend to create ion trails, meteors, things that streak across the sky. When those burn up, they generate a lot of heat. That heat ionizes the atmosphere, causing an existing trail that may stick around for 15, 30 seconds. And your signal that goes up, typically on the 6 meter band, might actually come down somewhere and somebody else can hear it. They're probably not going to be able to respond off the same trail, but if they heard you, if you know there's a meteor shower going on, they might be aiming up at the same area, and 5 minutes later you get a response. Like, hey, we talked off of meteors.
That is cool.
Yeah. Let's see, other stuff. As far as long distance propagation and times and things like that, I think I've always thought that this was somewhat instructive. I'm going to open up a website. One of the things that we do is we use something called PSK Reporter for a lot of the digital modes that we use. The digital modes, again, this is all, ones and zeros and things like that. And one thing that we do is hybridization of the internet and radio, which is always something, that if you can do it, it can be really cool. Received by Grid Square CN84. Okay, so this is in the area where we live. These are active reports that people have made by frequency bands on different bands and different wavelengths. So showing the day-night terminator, certain bands, certain frequencies seem to work better. There's a good opening from the West Coast right now to South America. I believe that's on 10. Yeah, that's on the 10-meter band. But you look at these other ones, for instance, to Japan, the sun hasn't come up there yet. So that's on 20 meters, which is 14 megahertz. So there's not enough ionization for that really high frequency to work there yet. Similarly, if I were to go to, let's say, Germany, we might see a completely different map. Come on. Okay, notice we have a completely different map, different colors, different bands are active, and they are these dark colors, 40-meter band, 80-meter band, which are very low frequencies, 30-meter band, because the sun hasn't been up for a while. You actually have a visible change looking at the screen, there's actually a visible change in the frequencies that work and don't work. And we played through that every single. Questions on that before we move? Okay.
Yeah, yes, I do have one, and
Yeah.
I was looking at that you had called up. How do you determine your grid for where you live? And then the second question is, it sounds like when you were looking at that, you could look at it kind of in real time and say, I'm better off right now
absolutely
being on 20 meters instead of 40 meters or whatever.
Yep. The other thing is that so as far as finding your own grid square, it's based on latitude and longitude. You could figure it out yourself. Everybody should know, if you have a license, you should know your own grid. You should know your own grid. It's important to know because if you operate on the VHF bands, everybody cares about the grid that you're in. The easiest way to find it is you open up, if you have a license, you're in QRZ, and if your address is right, it'll show you what grid you're in. The other one is if you have on your phone, if you use the repeater book app and open it, it'll show you exactly what grid you are in at that time.
Oh, that's interesting.
Yeah. That's when I land somewhere on a plane. That's how I figure out what grid I'm in. It also shows you a list of all the nearby repeaters within like 50 miles.
Okay, I got it open. All right.
Yeah. Okay, cool.
Thank you.
Yeah. So let's see other stuff. With regard to propagation. Okay, so propagation is how signals go from one place to another. And propagation is always going to follow some basic rules, but at the same time, not. Right? The basic rules are that, for instance, if you have propagation is just basically what the atmosphere will allow radio waves to do, what the local terrain will allow radio waves to do. However, for instance, if I look at something called VOACAP for ham radio, this was actually developed by the Voice of America, Voice of America being the United States federal government's voice to the world. So now let's see, if I were to pick a certain power level and say between the United States and somebody give me another place. Anywhere in the world.
Norway.
Prague.
Where?
Norway's fine.
Norway's fine. Okay. Between the US and Norway. Here it is. This shows me statistically, given the power levels and the antennas that I am using and the time in UTC, notice it goes 0, 1, 2, 3, 4, 5 around the clock, and the bands in wavelength, 10 meters, 12 meters, 15 meters, etc. This shows me the probability of being able to make a contact in those particular places, given modeling of all the conditions at that time. And again, this is something that it was paid for by the government to work for, to be used by Voice of America. And somebody modified it. Yeah, super helpful. If you're trying to make a particular contact, let's say you're trying to work, this will look totally different. Southern Argentina. Map looks totally different. Right? That's your schedule. You want to make a contact in Western Australia? You want to try going the long way. It'll show you the short way or the long way. So incredibly powerful tool. And this is why, for instance, the Indian Ocean is very difficult to contact, for instance. Although, wow. Okay, I might actually have to try. Sri Lanka is particularly difficult for a lot of us. Pakistan is very difficult. Yeah, there we go. It's mostly a land route, so that's why we almost never hear them. All right, so lots of propagation tools out there, and that virtually all of them are free to use. Let's see other stuff. So if we start looking at Oh, heck. We start looking at VHF, UHF. Remember I said that VHF and UHF were largely line of sight. So let's say we have a person standing here and a person standing here. I love my drawings here. Here we go. Here's a radio. Here's another radio. Okay. Would everyone say those are basically line of sight?
Yes.
Yeah.
Okay. They are line of sight, right? Because there's nothing in between. How about if I do this? And there's a hilltop in between them. Line of sight anymore?
No.
Nope. Okay. So how do they communicate with each other?
Repeater.
Okay. There's a repeater. You could have a person standing up here who has a handheld radio. This person talks to this person, and then this person relays the signal, and vice versa. That would be the simplest form of what we would call a repeater. You could also replace this person up top with an automated box that had a receiver and a transmitter that would do the exact same thing as what I just drew that person doing. That's known as a repeater. It literally repeats the signal. How about other things? Other ways to do this?
That.
Well, you could also send a signal, if you had enough power, right over the top, and then you get something called knife edge diffraction, which comes directly out of physics, which causes some of the signal over a sharp corner to diffract downward. So that's known as knife edge diffraction. Now, here's another one. We had one of our guys in our local radio club who was up in the mountains, and he actually was trying to get into our local repeater to talk to us. And he was up by Mount Hood. And so Mount Hood, I'm going to try to draw this as there we go. There's Mount Hood. He actually sent a signal backwards, the wrong way, which bounced off the mountain, Mount Hood, because it's 11,000 feet tall, and managed to talk to us by intentionally bouncing a signal off of a solid object. That works too. That could be a big building, for instance. This could also be a satellite that can serve as a repeater. Satellite might have a repeater built into it. The International Space Station actually has an onboard satellite repeater, which is open to any ham who wants to use it. There are also dozens of other satellites up there that are carrying repeaters. So lots of cool ways to get signals from point A to point B. Now, one of the issues, of course, in dealing with this is that radio waves, again, they follow line of sight. But what if there are more than one lines of sight? Okay, we already said that sometimes a signal will bounce off of a solid object intentionally. Sometimes it'll bounce off a solid object and it's not intentional. So here's a person with a radio, and here's another person with a radio. Here's the direct line of sight, but here's a truck overhead parked by the side of the road. And you have another signal, the same signal.
Picket fencing?
So now you have, well, the truck isn't moving. Now you have two different paths. One of them is probably better than the other, but maybe not. So if you don't have a direct line, maybe you're using the truck on purpose, but maybe you're using the truck by accident and you actually have two different paths to get there. So let us say that this bottom path is n wavelengths in length. And it doesn't really matter what that value n is. Let's just say that for whatever reason, this other one is n plus 1 wavelength. What does that mean? It will travel 1 wavelength further to get to you. Well, this one looks like this. This other one looks like this. Well, that's fine, right? They're getting there at the same time. One's a little later than the other, but you're seeing them both at the same time. This is constructive interference. This is a good thing, or at least not a bad thing. But let's say that that other path is n plus 1/2 wavelengths. That means that that other one is going to arrive like this. What's going to happen to those right there? Considering they add together, what's going to happen?
You'll get a lag.
Echo.
They're going to cancel out.
They cancel each other out because they're adding together. They cancel each other out. So if they cancel each other out, what do you hear?
Nothing.
Nothing. Okay. But now let's say that you can actually move a little bit so that this is no longer n plus 1/2. It's actually n plus 2. Well, okay. It's getting there a little late, but they made them that they both got there. The peaks are lined up, and all of a sudden you're good again. You'll be hearing something. If you move again, and this is now n plus 2.5 wavelengths, is that good or bad?
Bad.
Bad, because that half wavelength causes cancellation. It may not be the exact same amplitude, but basically you get strong spots and weak spots. If you're driving a car, this is known as picket fencing. If you are standing in your house, what you'll find is that, let's say that you're on the 2-meter band. How long is one wavelength? Not a trick question.
Meters.
2 meters, which means that's about 6 feet. So if you were to move this way, let's say 3 feet, you might find that you went from an area where you didn't have coverage to the point where you do have coverage. It's physically just the act of moving a couple of feet might take you from a bad spot to a good spot, or a good spot to a bad spot. What if that truck was replaced by a different truck? Yeah, then it becomes unpredictable, and that actually happens too. Okay, let's see. This is known as multipath interference, where you have a signal that goes that way, and another one that goes that way, and potentially another one that goes that way, and another one that goes that way. That's known as multipath interference, and it's typically not a good thing. It typically leads to conditions where, you know, if it's a destructive interference, it'll ruin your reception. So now let's say that instead you have a house with an antenna on this. Okay, and you are talking over long range. And your antenna is between 2 trees. And so is the other person's. So here's your antenna hanging between 2 trees. And the frequency band that you're on is 40 meters. So your antenna is 66 feet long. All right. If somebody starts to fade in and out, what can you do about it?
Move slightly.
How? Your antenna is 66 feet long and up in a tree. What do?
Change the angle?
You can't.
Oh, no.
You do nothing. You learn to live with the fact that that this ionosphere that we are using, it changes in height. It's not like a mirror. It's bumpy and shifts and has all these little lumps. And when you're listening, if you're, for instance, if you're, let's say, talking to somebody in Russia, or in we mentioned Norway or Finland, and it's going over the North Pole, which means it's going through the aurora, that signal sounds really distorted. I mean, it's warbling in and out and fading like crazy because that's what the atmosphere is doing to it. and you have a fixed antenna and they have a fixed antenna, and there's nothing you can do about it. It's just one of those things that happens. All right.
I've encountered a unique situation with my trusty Baofeng that on a simplex net, it's almost line of sight, but one guy I can't hear. I hear everyone else, but this one guy, and I found by turning my radio sideways, hear him fine.
Isn't that funny? Even though
I have
his
no
is
idea
not,
why.
we're getting to that right now.
Oh, very good.
Yeah, because it shouldn't work, but it does somehow. Okay, so I promised we would get back to this. So this is your oscillation of your electric field. Okay, so here's your electric field. It's oscillating in the vertical direction. This would be known as vertical polarization. The direction of change of the electric field is known as the polarization of a wave. The type of antenna that makes this particular wave would have the same polarization. So to get a vertically polarized wave, which is the electric field in the up and down direction, perpendicular to the surface of the Earth, that would be a vertically polarized antenna. The most common of these is a vertical antenna, just straight up and down. The electrons move back and forth this way. When doing so, they generate a vertically polarized electric field. An electric field that is horizontal, parallel to the ground. Any idea what that would be called?
Horizontal.
Horizontally polarized wave. That's right. An antenna, a typical antenna that makes this is a dipole antenna, which is parallel to the ground. Okay. So now we are into antennas. But before we do that, we're going to take a short break. But I want to mention the fact that if you have a wave that's generated by a vertical antenna and it is oscillating with the electric field in the vertical direction, if you are line of sight and you have a horizontally polarized antenna, the up and down electric field that this is generating will have very little effect on this antenna, which is why typically your polarization of your antennas on both ends have to match. But as you saw, that's not necessarily true, because when radio waves hit stuff, their polarizations can be randomized, they can be rotated, they can be turned 90 degrees, they can be made elliptical. You can end up with, like, if you've ever seen polarizing sunglasses, they can do stuff like that. It can change from random polarization to one direction, or one direction rotated 90 degrees and continually rotating, depending on what it hits. All right, any questions before we go to break? 5-minute break, okay?
Can you you have an antenna that is polarized both vertically and horizontally?
Not specifically, but if essentially it's circularly polarized. So if it's random, it'll have both characteristics. You can also have one that generates a polarization that makes a spiral as it travels forward. And you can have a right-handed spiral or a left-handed spiral, and those are called circularly polarized. That's often what we do with satellites. And they'll specify whether they're right or left-hand circularly polarized antennas when you're trying to talk to them.
All right.
Can
All
you
right,
go on like a little bit of a side tangent at some point on satellite stuff? I'm a student studying like satellite communications for cybersecurity, so like that's cool stuff.
I might have to drag somebody else in to give you as many answers as you want.
Okay.
Where are you going to school?
So I'm a student at Western Governors University, but I'm also doing my own independent research. Currently, right now, I'm doing security reverse engineering for like CCSDS communication protocols. So just standard satellite telecom stuff. But I want to talk to satellites. So
Yeah. All right, I'll be back in a few minutes.
Are you still there? The satellite question person, are you still there?
yes, I am.
Well, basically, the satellite, because the satellites rotate, circularly polarized signals are the best way to reach them because, like you were saying that, if you say you're using a handheld to talk to the space or to a satellite, if you just had I don't know, a whip antenna that's kind of pointed upwards,
yeah,
the satellite's rotating. So the best way to get the signal from your radio to theirs is to have both antennas in the same polarization.
Okay.
Because if they're cross-polarized, you'll get a big reduction in the signal strength. So, and as the antenna is rotating around, if your antenna is stationary, then your signal is going to be in and out. You know what I'm saying?
Yeah.
At the frequency of the rotation of the satellite. So, typically, the best satellite antennas are circularly polarized, so that the signal, when it reaches the satellite, of course, is rotating much faster than the satellites. It's rotating at the frequency of the signal. Could be 140 megahertz or 400 megahertz, something like that. So it's going to constantly be intercepting the satellite antenna at the proper orientation. That's why circular polarization is really useful for satellite communications.
Noted. I will be looking into that.
Yeah, look into I mean, that's a whole branch of ham radio. I was gonna think of a good. I know a couple of really good introductory videos. This stuff is not hard to do. I mean, when we talk about making a circularly polarized antenna, it basically is. He's going to probably talk about specific types of antennas, but there's antennas that they look like TV antennas. You can imagine like what goes up on a roof.
Yeah.
And so they have like a boom, and then there's a bunch of these elements that stick out sideways from that, and they change in size. Maybe I'm sure you've seen those kinds of antennas.
I think is it like what they call it, like a Yagi antenna? Is that
exactly? I was gonna say a Yagi
okay?
antenna.
I'm fairly up to date on like most of the antenna styles. So a Yagi then.
Yeah, picture a Yagi, but instead of just having only say horizontal elements, also vertical elements that are sticking up. So those elements are 90 degrees quarter wavelength away from the horizontal elements, and there's maybe a series of those: horizontal, vertical, horizontal, vertical, horizontal, vertical. So as the signal moves forward down the boom, it encounters, say, a horizontal one will encounter the vertical one, and the vertical one will set it into a rotational motion, and then it gets reinforced by coming up against a horizontal one, and then another vertical one. So it's like adding a vertical and a horizontal together, and then you'll see like a circle form.
Yeah.
Okay. So it's a sine wave going horizontally, one going vertically. They add together, they form a circle. So that's kind of how it works. So actually, what it is a spiral coming off the antenna.
I was gonna say, like, if you usually like if you take a sine wave and you extrapolate it like in a three-dimensional sense, it is essentially just making
exactly
a circle, and it's just propagating through the antenna that way and calculating it. At least
exactly.
Scott, would that be a helix?
Yes, it's exactly that. There you go.
Yeah.
Perfect.
Word.
Yeah, it's a perfect example.
As
okay,
opposed
yeah,
to,
that makes perfect sense then.
Yeah, as opposed to linear polarization, which is one plane.
Exactly.
That's cool.
Yeah. So for satellites, it's circular or elliptically polarized waves are much more useful than just a scanning. And also, by the way, in FM and TV broadcast antennas, you'll see. I think there's some examples there of circularly polarized antennas for those applications as well. Because if usually in a large city or where there's a lot of terrain, it's better to you get a lot of shadows. When the antenna is going to be broadcasting into a city, you get a lot of buildings that get in the way. They create shadows. With circular polarization, it actually kind of negates that. So a lot of these broadcast companies will use circularly polarized antennas for just terrestrial, ground, FM, or TV transmission as well. So that's another application.
There we go. That's what I needed.
Yeah. Sure, but for your satellite interest, yeah, that's the main reason because of the rotation of the satellites, and so
Love
it
it.
works better. And I
Yeah, the other
believe,
Thank you.
yeah, sure, and I believe the same thing is true for the deep space probes that go out to Jupiter and Mars and beyond.
Yeah.
Yeah,
they're also
the other thing is that, like you were saying, if you have a circularly polarized wave, it has horizontal and vertical components,
right.
Mhm.
which means it doesn't really matter what your antenna is. If it's linearly polarized, whether it's vertical or horizontal, it'll still hear it.
Exactly. Yeah.
It'll be a little diminished, but who cares?
Yeah. The main thing is you'll get a much more smooth transmission reception using
Yeah, that
that
makes sense.
for satellites anyway, and probably space
Interesting.
probes.
Interesting.
So Scott, are we going to continue till 2 p.m.
2 o'clock.
Pacific?
Yep,
Okay.
2 o'clock.
All righty.
Okay, we're into antennas now. Woohoo! Okay, so here we go. This is the fundamental antenna. It's a half wavelength long. It's typically fed in the middle. This is known as a dipole. And because it's fed in the center, it's a center fed dipole. Now, one important thing to note about an antenna is that it has to follow the rules of physics. So if this is just a piece of wire, or really in this case, two pieces of wire, which it is, what is the current at that end?
Zero.
It has to be zero. What is the current at this end?
Also zero.
Also be zero. It also has to be zero. So no matter what's happening in here, those boundary conditions where you have zero current at the end of the wire, physics says that unless you have current flying off into space, which you typically and hopefully don't, you're going to have zero current there, which means that we can actually start at this point, and we know that if our antenna is a half a wavelength long at the whatever wavelength we have chosen, this is a wave. Everybody agree with that?
Yep.
Okay. This antenna will be optimal to do this wave shape so long as it gets to the peak. And we can actually draw it like this. It gets to the peak and then goes back down to zero. This is our current distribution. Notice it meets the boundary condition, which is zero current at the end. Everyone agrees with that, I hope. No current at the end.
Yeah.
And actually maximum current in the middle. So what makes a magnetic field? Current. Maximum current right in the middle of the antenna, which means that you're generating lots of magnetic field. If you're generating magnetic field, you're generating an electric field as well, which means that this is the first antenna starting from smallest to biggest that actually works well. This is the best first antenna. If I were to make this shorter than a half wavelength, let's say that instead I made this antenna a quarter wavelength long. Well, here's my wave. Right? What is my first thing that has to be met? Current at the end has to be
Zeros.
Zero. It's still on the
So I
way
got a
up.
question.
Yep.
Does that mean so if you're wanting to transmit, let's say on 6 meter, you would need at least a half that antenna?
You don't necessarily, and we're getting to that.
Oh, okay.
Okay. So
Or that would be optimal, is what
that
you're
would
saying.
be the first position that's optimal. So what happens?
Okay.
Can you keep going up at this point? No, because at the other end you have to do what?
Zero.
Zero, which means that even though your peak would be about like here, this can't exist because physics says it can't exist. Same over here. So you never get to the peak, which means that this antenna is suboptimal. So that is typically why we never start with anything shorter than a half wavelength.
And Scott,
Yeah.
this is why your 40-meter connection earlier had a 66-foot antenna.
That's exactly right.
Right?
That's exactly right. Yep.
Oh, good.
Yep. Okay, so now we can take the same antenna and make this a half wavelength long and do this with it. Doesn't really matter where we feed it exactly, not too concerned with that. It's a half wavelength long. It has a peak current somewhere in the middle. There's zero current on the ends. This antenna is basically what you'll find inside every directional antenna or most directional antennas. Essentially, what you've got from this is a radiation pattern that follows in the shape of a figure 8. Kind of makes a donut around the wire. So, very important to note, there is no radiation coming off the ends, or virtually no radiation coming off the ends.
Are we looking down?
We're looking at it from the side.
Side.
I'll try to make a better donut. It's actually a toroid. So basically there's energy coming out there and down and up. Okay, so there are certain issues with this. What happens to most of the energy that is going straight into the ground?
Lose it.
Hopefully it bounces back up, but very often it doesn't. How about stuff that's going straight up into the sky?
You lose it.
It goes up into the sky and you don't see it again. Right. The angle's too steep. This can be useful for certain things, but for the most part, it's really not. But a dipole is a really good start. So it's the basis for an antenna that we call a Yagi, which is a directional antenna, which has a dipole as the driven element where we feed power into. And then we have a reflector, and then we have a director, or potentially multiple directors. As we feed energy into this, the big element in the back takes the energy that's going backwards and re-radiates it forward, and these smaller elements toward the front make a more preferable path for energy to flow in the forward direction, which means that instead of looking at it from above, instead of looking at it like a figure 8, you now have a pattern that is much more pointed in the forward direction and a very small lobe in the back.
Sure.
Okay, so how there's zero current at the end, but some current in the middle. Okay. Well, we have to think about what current is if we want to discuss that. What is current? I mean, what is current? What's the definition of current?
Pushing electrons around.
Right, it's movement of electrons. How much movement can you have at the end? It can't. There's nowhere. Every electron that's going that way has to be countered by another one going back the other way. So the net is 0. So you might have current flowing this way and current flowing this way, and then it changes direction and goes back that way and goes back that way.
That's AC current.
Yeah, it is. We're dealing with RF. Radio frequency has a frequency, right? It's AC. So it has a frequency. It has a wave.
Yeah, I didn't know RF went back and forth like that. That's cool.
Yeah, it has to. It has no choice. It oscillates. It goes plus. It goes minus.
So it's like pushing electrons into the wire and then taking them out again, kind of?
Or pushing them in one side and out the other, back and forth. So that essentially you get a current distribution traveling down one way and traveling down the other way. So because that's a half wavelength long, let's take a look at, is there any reason we couldn't do an antenna that looks like that?
No.
No,
No.
it's a half wave long. Okay, so what's the good thing about this antenna?
Directional.
Yeah, well, no, it's not directional, but its lobes look like this. So they make a donut shape like that, and it's horizontal.
Oh, I see.
That can be really helpful, right? Especially if you want to talk to somebody there or over here or over there or over there. It's an omnidirectional antenna, and it's vertically polarized. And what's nice about this is that it doesn't waste a lot of energy shooting up at the sky, and it doesn't waste a lot of energy shooting down at the ground.
Could
What's
you,
nuts? Go ahead.
I'm sorry.
Go ahead.
I didn't mean to interrupt. Could you just briefly help me understand how an end-fed half-wave antenna, which generally will have like one end higher than the other, how it works?
Okay. So that's actually the next thing I was going to get to.
Okay.
All right. So, but don't let me forget in case I get sidetracked. Okay. So we're going to leave this half wave antenna and we're going to instead cut off the bottom. How long is it now?
Quarter wave.
Quarter wave. Okay. But if we feed it here, there has to be the bottom part of it somehow. It has to exist. Well, it doesn't physically exist, right?
Earth.
Well, this is a quarter wavelength long, and the bottom part doesn't exist. But if this is something metallic, and we have current flowing this way, then something has to account for the current flowing this way. So what ends up happening in this case is that this becomes, if you think of what a mirror looks like, if I was standing over here looking at this antenna and this was a mirror, what would I see?
The other quarter wave.
I'd see the other part of it, which is a reflected version of that top part. But I would not, and I wouldn't know if I didn't know there was a mirror there, that there was no other half. So to the outside world, this actually looks like a half wave antenna. There's the missing half of the antenna. It's mirrored in the bottom. And the tricky part is if you have let's say if you have a magnetic mount antenna, which looks like this. Here's your quarter wave up here. Here's your ground plane. That's the roof of your car. There is no electrical connection with that ground plane. Would everyone agree with that?
Right.
You didn't have to drill a hole in the roof, right?
Right.
Okay, but what there is the center conductor of the cable goes this way, and the outer part of the cable, the shield, goes this way.
Mind.
Okay, so what does that make? What do you see in there? Right in here.
Transformer?
Nope. What do you see?
The ground?
You see two metal plates with a space in between. That's a capacitor. That's a capacitor.
Oh.
And what did we determine about a capacitor at very high frequencies? Looks like a capacitor looks like a short circuit. So as far as your car and the roof are concerned, you have a short circuit right there. The roof is connected capacitively to the base of the antenna. If you've ever seen an antenna that that looks like this, here's the window of your car or the windshield or the back of your car. You have an antenna that goes like this. And on the inside of the window, you have another plate that looks like that. Anyone ever seen a through the glass antenna?
Yes.
Yes.
Yeah. It's been a while. Yeah.
Capacitive coupling through the window. through the glass. So clever. Capacitive coupling through the glass. Okay, so let's talk a little bit about impedances.
So capacitive coupling is not the same as inductive coupling, right?
Nope. Nope. It's just electric field generated and passing current and passing a voltage from one side to the other. Okay, so let's talk about impedances. Okay, so how you feed an antenna is very important because you have to, an antenna is really just a piece of wire. How you get power to the antenna is very important. This is known as a feed line. This can be in the form of coaxial cable. This can be twin lead, which is just two wires separated by a space. But what's important is that the feed line ideally is separate from the antenna. Right here at the center of a dipole, the impedance is about 72 ohms. And notice its impedance. And now is a good time to talk about impedance. We started to talk about that with reactance before. Okay. There's something called resistance. What do we measure resistance in? What units?
Ohms.
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 Okay. We have this thing called reactance. We measure that in ohms. Okay. This is what I would call a little bit beyond the level of class, but still very important because because it's brought up. Resistance is the ability of something to resist DC. Reactance is the ability of something to resist AC. And that's why there was that frequency component in there. Minus 1 over 2 pi fc or plus 2 pi fl. Notice that F, frequency. Z is on the complex plane, it's equal to R plus IX. And if that doesn't make any sense, that's okay. What it means is that these are perpendicular. So this is the resistance number, and this is the reactance number. And what's significant about this is that if I have, let's say, 3 plus I4, and that's my impedance, it might look like this. 3 and 4. These are at right angles to each other. What's the length of the hypotenuse?
5.
That would be 5. 5 ohms and an angle between the resistance and the actual result. So it would have a magnitude and an angle.
45 degrees.
No, not this one. It's about 58, I think. If it were 3, it was 3 and 3, it'd be 45 degrees. But that would be 5 with an angle, 5 ohms with an angle of about 57, 58 degrees. What's significant about this is that this is our impedance. This is how that circuit would respond. And if I were to take a look at Ohm's law, E equals IR, does everybody remember that?
Correct.
Well, I'm going to mess it all up because actually it's not true. E is actually equal to IZ. Normally, we don't consider the X part, so that simplifies to E equals IR. But if we're doing it thoroughly, we end up having to deal with the fact that there's an angle in there. And actually, that's what causes a phase shift because there's an angle built into it, and that causes the current and the voltage to have a different phase. But anyway, so now that we've talked a little bit about impedance, that's impedance. A dipole antenna has an impedance of 72 ohms. And fortunately, it's mostly resistive. That's called radiation resistance. Okay, so 72 ohms. That is our impedance. That allows us to deliver maximum current And our voltage profile looks something like that. So we have our current and we have our voltage, and we deliver our maximum power right at this point at 72 ohms. What's interesting is we can also not care where we feed power into this thing. The only rules are that we have to deliver zero current at the ends. Well, if we feed it all the way at the end and we're delivering zero current, that's not going to work because you can't deliver no current. I mean, I guess you could, but it's very difficult. But we could be just a tiny bit away from the end point, break the wire right there, in which case our feed point impedance would be about 2,200 ohms. Because, remember, E is equal to I times Z. So Z is equal to E divided by I. In this case, it's about 2,200 ohms, which is very, very high. But remember what we talked about very briefly this morning. What is this thing called?
Inductor.
Two inductors back to back around a coil, around a core. That has a name.
Step down transformer.
That's a transformer. And one of the things that I mentioned was that a transformer can change voltage, but the other thing is that it can change impedance. And the impedance is proportional to the square.
The turns.
The square of the number of turns ratio. So if you pick a number of turns that 2,200 ohms is on one side and the other side gives you 50 ohms, which is what most coax cable is, then you're good. That is what is inside your end-fed half-wave antenna. Okay, who asked the question about the end-fed half-wave?
I did, John Perry.
Does that answer your question about the end-fed half-wave?
I'm trying to digest it. I took a screenshot, so I'll look at it later. I don't want to hold it up.
It's an impedance matching transformer.
Okay.
That's built into it.
So basically it's your coax. Is that what you're saying? The 50 ohms from the coax?
Well, the antenna impedance is 2,200 ohms, period, because of how it's built. The fact that you have a transformer that is probably 49 to 1 or something impedance match.
You're talking like the balance and the ununs and stuff.
Yeah.
Okay. All right. Now I'm tracking.
It functions as an impedance matching network, which transforms it to 50 ohms, which is what your coax typically is.
Oh, okay.
Thank you. Okay. So now we're going to briefly talk about how you compare one thing to another. We'll call it the ability of one thing to function compared to something else. So let's say that I have this circle and I have this circle. How many times wider is this circle on the left than the circle on the right?
Lots.
Approximate. Give me a guess.
1,000. 30.
Okay, so let's say 30. Okay. What if I were to shrink this down? How many times bigger is the big one than the small one?
300.
Yeah, okay. How about if I replace that again with like this?
3,000?
Yeah, okay. How about if I made this one even bigger? What do you think?
1,000,000.
Okay. How about if I were able to make this one infinitesimally small as I could possibly go? These numbers are starting to not make a lot of sense, aren't they? They're getting kind of silly, right? At some point, you don't care what the exact number is. All you care is about is the rough order of magnitude. Okay, so we're going to move into something called decibels. Okay, so this is a way of comparing something with something else, sort of like how we compare an earthquake's size, and it's a logarithmic scale. So it was, if picture this, if you have a signal, which is over here and is this big, and the signal that's over here that made it goes through some kind of black box to make this really big signal. You want to know how much bigger that big signal is compared to the one that started, to know what this black box did to it. So let's say that this is 1 unit and this is 1,000 units. It made it 1,000 times more powerful. It made it 1,000 times bigger. Well, you could say it's 1,000 times, but okay, let's say it's 1,000,000 times. Let's say it's 1 billion times. Let's say it's 1 trillion times. At some point, again, these numbers don't make a lot of sense. However, if you could say, okay, well, let's look at it logarithmically. This is 10 to the 12th bigger because that's 1 trillion times. Well, if I could then take this value and just say, well, okay, we'll call it 12. Well, if I took another one and it was only 1,000,000 times, then that would be 6. This is the basis of the decibel. It deals with the exponents of this really big value or really small value. I might have 0.00000000001, which is 10 to the minus 12. I would call that a minus 12. So the foundation of this is a way of comparing one thing to another. It's a log base 10 of something versus the original thing. Well, as it turns out, these numbers ended up not being quite big enough. So that was known as a bell. They multiplied that by 10, and that became tenths of bells, so decibels. The function is 10 log base 10 of P2 over P1. The nice thing about this is that if something is 10 to the 12th times bigger or 1 trillion times bigger, the log base 10 of 10 to the 12th power is 12. That's what logarithm means. The power to which 10 would have to be raised to get it. Okay, so I have 10 times that is 120 dB. We use this as the basis for calculation for everything from antenna performance to cable losses to amplifiers to signal strengths to, basically how much path loss there is between 2 points due to being 5 miles apart with a whole bunch of trees and leaves in between. So there are really only 2 things that you have to know that this simplifies to. A factor of 10 is exactly equal to 10 decibels. Similarly, 1/10, because it's exponential, is negative 10 dB. And 2 times is approximately equal to 3 decibels. And 1/2 is approximately equal to negative 3 dB. And again, this comes from exponents, powers of 10. What's convenient about all this is that, let's say I have a station which is transmitting with a transmitter, which is 100 watts. Yeah, let's call it 1 watt just for the heck of it. This is going to be the last thing we do today. Okay, so that's transmitting with 1 watt. Okay, compared to a milliwatt, how many times bigger is 1 watt? 1 watt compared to 0.001 watts. How many times is that?
1,000.
1,000 times. Okay, so 10 to the watt power is 1,000.
10.
3.
Well, what?
3.
Well,
3.
Right. So logarithmically, that would be decibels
Oh.
is 10 log base 10 of 1,000, which is 10 times 3, which is 30 decibels. Okay. So this signal 1 milliwatt compared to a milliwatt is itself is 0 dB compared to a milliwatt. This 1 watt here would be 30 decibels compared to a milliwatt, or 30 dBm. What's cool about decibels is that they just add together. The reason they just add together is if we, for instance, if I ask you what is 10 to the second power times 10 to the third power, what is that?
10 to the fifth power.
10 to the fifth power. Exponents just add. And because I'm working with exponents, if I'm multiplying things together, I'm just adding the exponents. And decibels are a function of exponents. So if I have...
Question on that.
Yep.
If they just add together, how is if you add 3 dB, do you double your power?
Because 10 log base 10 of 2 is approximately equal to 3 dB. If you go through and take the logarithm base 10 of 2, it's actually 0.31. Because 10 to the 0.31 power is about equal to 2. This is a way to never have to go through that painful math. So let's say I have a piece of cable that has a loss of -2 dB and an antenna with 12 dB of gain, and it travels through space, path loss of a -120 dB, and another antenna with a gain of 7 dB, and a cable with -5 dB, and here's my black box. The question is, how much signal makes it down to the black box? So I'm going to start at 0 right here.
10.
Okay, so I'm going to just go through the thing. Is it plus 0, plus 30,
8 dB.
minus 20, or sorry, minus 2, minus 1, plus 12, because I have 12 gain, minus 120,
78.
plus 7, minus 5. Do we all get the same answer? 28, 40, minus 80, minus 72. Oh, wait, minus 73, minus 78. Did we all get that?
Mm-hmm.
Minus 78 dBm.
Yes.
Okay,
Yeah.
that is the signal strength by the time the signal got down to this point. Did I ever have to multiply anything by ugly factors of 10 ever?
No.
No. Decibels are a way to avoid ever having to do that. And because virtually every device, every component that you will ever find, path loss, anything in, let's say you have a receiver and it says I have a sensitivity of minus 120 dBm. That's how it's actually specified. So if I have a signal strength of minus 78, do I hear the signal or not?
Yes.
Yes, because minus 78 is a bigger number. It's more positive than negative 120. There you go. I just went through that whole calculation, and instead of having to take all these little, all these values like 1,000 and figure out what minus 2 decibels is, whether it's like 0.4 or whatever, and having to multiply them all together, I just added all the decibels together. It was a brilliant innovation that came out of signal design, system design. So that's going to be it for today. Does everybody remember these two things? These are the only things you have to remember. And if we're looking at, there's something called a half power point. Half power point is known as -3 dB.
Not necessarily, but if you get it uploaded to YouTube tonight, I'll watch it before you start tomorrow, because I'm on the East Coast and I wake up very early.
Yep. Okay. And I'll hang around for a little bit to answer questions too.
And you're gonna send out tonight the links to the YouTube.
Yep.
Scott, I apologize for missing this. What does that end computation of a negative 120 dBm? What is it saying to me?
This is a minimum discernible signal. It's called a minimum discernible signal. In other words, because it's dBm, that is compared to a milliwatt. So in other words, this receiver right here, this black box, has to be able to, it can hear anything that is less small or bigger than negative 120 dBm. And negative 120 dBm is this much of a watt. That's why we use this stuff. That's why we use decibels. Yeah, 10 to the minus 12 milliwatts. This is actually very typical. In fact, that's actually more than you will typically see. Receiver capabilities. Like a lot of receivers that are available today, you'll see a minimum discernible signal of like minus 133 dBm, which is 0.000
Maybe
2 or so watts. That is how much power is actually getting to the receiver by the time you can actually still hear it. So if you look at this and realize that somebody on the other end put out 100 watts into an antenna, and they had a kilowatt amplifier, right?
Okay.
And that went up into an antenna that had like 10 dB of gain. And all that made it out of there was this much power that made it back to your antenna by the time it got there. That effectively, you had 1,000 watts going out. So you had an effective 10,000 watts going out into space. And this is the amount that got to your antenna, but you can still hear it.
That's impressive.
That's amazing. That's almost impossible to conceive of those numbers. But that's what we do every day. When you turn on the radio and you hear a signal that's bouncing in and it doesn't sound very loud, and you realize that it's on the order of picowatts, that there's virtually no energy there. But not only can you hear it, but you can amplify it using all those transistors and all those tuned circuits, and everything in between point A and point B is able to bring it out into something that's audible. I mean, it's mind-boggling. You know, like this right here.
Is there a service that decodes that Morse code like automatically so you can hear what they're putting out?
You could ask me. Up.
Yeah, can you do me? Because I can't
30
do
meters.
Morse code.
Weather is overcast and 0C. So back to you, Dave. VE3UZ, JM3OLW, JM7OLW. So a guy in Canada talking to a guy in Japan.
Impressive.
I've never seen anyone do like Morse code. That's something my generation tends to do. So that was impressive.
That was
Actually,
impressive. Just like right off listening to it.
Actually, there are a lot of youngsters who do a lot of Morse code, actually. Kids like Morse code.
It's cool stuff.
Kids really like Morse code because it's a secret language.
I mean, I could take a Raspberry Pi and program it to listen to that feed and do it for me, but that's impressive. Just you hearing it and doing it.
Actually, yes and no, because your Raspberry Pi would have to be able to fill in the blanks and the fades and everything. And, I actually decoding Morse code because there's no error correction built in is actually very difficult to to do it well.
Oh, interesting.
Surprisingly hard. I mean, I've seen Morse code decoders that if the signal is stable and crisp, yeah, it does a good job. But as soon as there's any distortion at all or any fade, they just sort of lose it and they have to resync. There's no decoder that's been come up with that works as well as the human ear.
Kind of like autocorrect on your phone. It can't do what a person can do.
Mm-hmm. Yeah, I mean, I do Morse code. I've done Morse code since I was 15. I'd say my whole life, but not quite. Still my most enjoyable thing to do.
Well, it was impressive.
I can go a lot faster than that. That was slow.
I'm just glad it's no longer on the test.
It's not on the test, but you know what? People find that they enjoy doing it, and it actually helps them a lot when it comes to making a lot of contacts. It gets through when a lot of other modes don't because of its power spectral density, which we're going to cover tomorrow.
Yeah, very low bandwidth.
Yes, very low bandwidth. Again, power spectral density.
How do you transmit it? Because all I can think of is, from my, childhood textbooks of having something you just tap on the desk or like.
That works. But then there's also, hold on. It should be one. Something like this. That's typically what I use. So what you've got is but I can only send it about 20 words a minute with a straight key. But you typically will hook this to an electronic keyer, which that's actually on the exam, which actually forms dots and dashes or dits and dots for you based on the lever that you push.
Interesting.
And I can do 35, 40 words a minute with that. Above that, you really need a keyboard. I make too many mistakes.
Very cool.
Any other questions? Keep them coming. Because you got Scott here, and Scott, I got to say, the other Scott here knows a lot of stuff too.
Scott, when the CW was on the test, how many words per minute did you have to do to pass?
The novice test was 5 words a minute. That was not bad. But then to get your general, you needed 13, and to get your extra, you needed 20. And I consider it still kind of a miracle that I got my 20, that I passed the 20 words a minute test. And actually in the process, I learned something, which was that was, I was 17 and I walked in and the examiners who were in college with me said, you should try the 20. I'm like, I can't copy 20. It's like, yeah, you should try it anyway. And they said, all right, fine. And it starts coming at me and I'm like, I can't write that fast. At that moment, I said, all right, I'm just going to write down notes. And I got 90% on the exam. Because I could understand it, but I couldn't write it that fast. I found out at that time that my limiting factor, and in fact, the limiting factor for a lot of people is the fact that they can't write everything down. But then I realized, unless you're actually doing like emergency communications where you have to write down entire text messages, the entire text, conversation isn't like that. You know, you don't write everything down that everyone's saying. You just listen to it. And it's like, oh, damn, it's a language. Oh, damn. If I just treat it as a foreign language, oh, I don't have to write anything down. I just assume that
the intent of the message, huh?
Well, no, I mean, I understand the whole thing. I just, you know, like if somebody's going to ask me what the guy's name was and there's a chance I'll forget it, I'll just write it down and scribble it down. So by the end of that, 5 minutes, I'd written down everybody's names. I'd written down where they're from and what the weather was and, important stuff. The rest of it was just filler. And I copied it in my head. I wrote enough down on paper that I got 90% on it. It's like, oh, that's how you do it. And actually, virtually nobody, including myself, virtually nobody teaches writing anything down. I actually discourage people from writing down exact text. I tell them just, write down important stuff, somebody's name and the gist of what you're doing, unless you need 100% copy. Just, have a conversation with someone. It's a lot more enjoyable that way. And you can essentially, there comes a point when there's the only thing that gets in your way is your ear's ability to discern stuff. If it gets into your ear and it echoes around and things blur together, that's a mechanical thing. And I'm at that point. I know where that is. For me, it's about 50 words a minute.
Wow.
I can still pull stuff apart, but I can't do it reliably. So
you said 50?
Yeah, like 50.
Wow.
You want me to show you?
Give us an example.
Want me to show you?
Give us an example.
Okay, I'm going to stop recording. Stop recording.